Okay, sounds like, okay, I'm good. So I thought we'd have some discussion on yesterday's talks. Any questions anybody wants to bring up? Because we have a kind of longer session today, if there are, I want us to ask questions, but if we finish a little early, I think that won't be a bad thing. So, but I'll give some time here for people to speak up.
Hey, so yesterday we heard a lot about more equation of state stuff. We had neutron tunneling and neutron stars. Talked about fast radio bursts. There's also symmetry energy discussions. Anybody have any questions, comments they'd like to add for any of the talks yesterday?
Yeah, I actually have a question, and it's about, so can you hear me? Because I also had audio troubles.
Yes, we could.
Okay, okay, good. So I have a question about phase transition. So when you make the phase transition to quark matter, and then I have the feeling that, you need to use some kind of transition density. And I was just curious about what we actually know already about this transition density, because some people use already at tri-saturation density. Yesterday in the talks, I saw something between 3 to 4 or even higher. So yeah, what do we know about this? And is there maybe also some systematic study? Because I guess the higher the transition density is, the less signatures you also see in neutron star merger simulations.
Is there any experts that can comment on that?
Yeah, so Andrew Steiner can't talk, but he put something in the chat.
Oh, I see, yes. Fortunately, my chat box is really small here.
So Andrew said there's pretty much nothing. We know it can't be near saturation density because we don't seek free quarks in the nuclei. So it sounds like it's a observation constrained thing where that saturation, where the transition density is. Is that true? Is there any theory predictions on it?
Okay, thanks for the chat messages. So I will have a look at the paper, but I guess this means that right now people are just using whatever whatever you like, or what you think is reasonable. Okay, thanks.
All right. Well, we do have a lot of speakers today. If nobody else has questions, we can go ahead and get started with the talks. Okay, I'll take that as a no. We can go ahead and get started with our talks. Is Nicole here? Just a reminder, the talk is going to be 20 minutes, and then I'll warn you when you have 5 minutes left.
Sure.
Okay. Okay. Great. Okay. So thanks so much for the introduction, and thanks for inviting me to the organizers. And today I'm going to be talking about the interplay between nucleosynthesis observables and the properties of neutron-rich nuclei. So what is the effect of this unknown nuclear physics in determining what we're getting from neutron star mergers? Okay, so I just wanted to echo something that Chris said earlier in the week, actually day 1, where he discussed how moving into this new era of multi-messenger physics and getting updates from LIGO as to merger rates and things like this are going to have led to the need for more precise predictions for what the R process is actually producing in something like a merger. So he alluded to this study here, which I'm going to show a little bit about how that is picked apart, all the pieces that go into this particular study. So for this study, what we were trying to find is whether or not mergers make enough our process material in order to explain what we see within our solar system. So what we did was to take estimates of the ejection range from GW 170817, couple them with ranges on the nucleosynthesis predictions, which we took different simulations for the conditions, as well as different mass models to get our abundances here. So this is an important step because if you're trying to determine whether or not neutron star mergers can make enough our process to explain the solar system, you really should not start from solar system abundances. You've sort of answered your own question if you start from that piece. So this is an important step. Those go into a galactic chemical evolution simulation, which then is going to determine whether we see a neutron star merger rate that gives us enough our process here. And you can see that this light gray band is what we got when we included these kinds of nuclear physics uncertainties. So clearly, as we get more and more refined estimates from LIGO, it's more and more important to be able to predict the yields from neutron star mergers. Now, I say that, but I would like to follow up with another example of where it's going to be important to understand your yields. And this is a case where this galactic chemical evolution actually almost entirely, the uncertainties involved in modeling galactic chemical evolution almost entirely come out of the mix. So what this was is a work that we published in Science earlier this year, where we wanted to take a look at the last R process event to enrich our solar system. So we looked at then radioactive isotopes, things with half-lives less than a gigayear, on the order of megayears and hundreds of megayears. And there are only 4 of these types of isotopes that they can have traces in meteorites of, listed here. And curiously, of the 4, 2 of them have almost the same half-life. So you may think, oh, wow, that's fun, but it's more than just fun. It has real implications here for the R process. So for example, if you take a look at iodine 129 versus iodine 127, something radioactive to something stable, you can see that a simulation, the ratio of these, you're going to inject some material and then it's going to decay and inject and decay. And so the ratio of these is time dependent. However, when you take a look at this iodine to curium ratio, given their similar half-lives, their ratio remains basically unchanged as you proceed within your evolution. Therefore, when you look at this ratio in meteorites, you're actually peering directly into the production ratio. So what was done by collaborators on this paper, Maria Geisler, Almudena Arconez, was to take a look at many different astrophysical conditions, as well as different nuclear physics inputs, and see what is this predicted ratio then, given current simulation, given some nuclear physics variations in very different conditions. And what was found is that basically things that are very, very neutron rich, such as these types of simulations here, produce ratios that are just way too low with respect to the observed value within meteorites, because we're just producing too much curium. And then winds have kind of a range of neutron richness here, and some of them can hit the sweet spot. And this particular simulation of MHD supernova just didn't make enough curium, actually. So you're higher here by too much. Now, we also wanted to just do some more tests of this. So what we did was with a different network. These were done with WinNet simulations, with a different network and with different nuclear inputs here, more models, as well as a different fission prescription. We took a look at really, are there any cases here that are hitting this, this measured ratio within meteorites? And we found that our calculations were pretty much echoing exactly what was seen within the WinNet calculations. The large majority of models are predicting a value that's just too low in this very neutron-rich ejecta, but we did find one that really did hit up here. So I would say that the message here is that very neutron-rich ejecta is disfavored by current nuclear physics models. However, if you want to connect back to sites, then we have to think about the fact that simulations are being refined all the time. So potentially these very neutron-rich components that we saw within these simulations could start to even out, maybe get pushed to the higher neutron-rich regions. Same with MHDs. Who knows what could happen here? That's still an active area of research. All of this is an active area of research. But what's exciting here is that since we take the GCE uncertainties out, we're looking at production ratios. So progress in simulation, progress in the nuclear inputs is really impactful for this particular ratio. So we just talked about dynamical ejecta a little bit. So I wanted to just remind us of some of the things that we saw earlier in the week from people that were discussing simulation, Jonah, Stefan, and Almudena, and others. And what was discussed is the effect of neutrinos plays a role here. Equation of state plays a role here in determining the type of ejecta, the type of neutron richness that you're getting out of such events. And we can see that you do have a distribution here of YE from something very neutron rich to moderate, and it's dependent on your inputs in the simulation. But a lot of these are still predicting for there to be a very neutron-rich component down here. So from the perspective of nuclear physics, this introduces some challenges that we have this very neutron-rich component, because under such conditions, you can have what's called fission cycling. So here on the right, we have, I have outlined where we have decay data. This is NuBase 2016. And you can see this is just an example of where we proceed, how far outside we are here. I'm going to play this movie where we're going to see the synthesis as a function of proton number and neutron number. But here the abundances are also going to be color-coded by the dominant reaction channel that they are undergoing at the time. So neutron capture, beta decay, fissions, alpha decay, etc. So you can see this is a dynamical ejecta, very, very neutron-rich condition. We get pushed up, we ride along the strip line, we get up here to where fission, we've pretty much washed away this first part of the pattern, fission is terminating the R process, and now we're depositing back into these regions. So when you look at this compared to this, you see how far outside of unmeasured data we're going. We're reliant on models, we're reliant on theory, and you could also see how your abundances are largely determined from the physics of these very heavy species, given that you push and wash away what you had down here in some cases with dynamical ejecta. So this is the kind of challenge that we're facing when we try to model dynamical ejecta from a nucleosynthesis standpoint. So one key input when you're determining your fission rates is the barrier height. So this is illustrated here. Basically, it determines the probability that you will fission. So low barriers, you're more likely to fission, etc. So these are two different models here. And what this demonstrates overlaid here is the R process abundances at a snapshot in time when your R process is terminating. That is when it has the highest mass number, average mass number that it's going to have over the course of the simulation. So you can see that here we encounter some low fission barriers early and we terminate, and here we just don't, and we can go even higher in mass number. So something like this has direct implications for the abundances that you get in the end, because you're accessing different nuclei with different models, different nuclei are fissioning, and the different way in which they split will come through within your abundances. Additionally, there are local effects from things here near N=126 and in the rare earth regions. So you do get very different predictions for your dynamical ejecta dependent upon your barrier model, your mass model, even with the same way that you choose to split that nucleus, which we call a fission yield. Here, I also want to point out that this gray band shows us a range for these particular calculations from just the astrophysics. So these were 30 conditions, all very, very neutron rich, YE of 0.01 to 0.05. However, they have different ways in which they freeze out. They have different evolutions for their density, different evolutions for their temperature, etc. So you do get some variations in what you would expect. So my take-home message from this slide is that it's challenging to model dynamical ejecta, and it's going to depend on not only your nuclear physics inputs, but also some of the specific astrophysics. It's not like if you have something very neutron rich, every time you're getting the same thing. Okay, so I alluded to the fact that we need to know how the nucleus splits. Of course, you saw that all of that material that went up into the actinides was getting populated back down and determining the structure of your abundances. So what we did in a paper a couple of years ago was to take into account for the first time that even in modeling the yields, not just the rates, there is an energy dependence. You have yield needs for neutron-induced fission, beta-delayed fission, and spontaneous fission. And this plot here demonstrates that the purple is what we got for spontaneous fission yields from the GAF 2016 code. And the red is what we get here when we take into account an excitation energy for neutron-induced fission yields. So you get some enhanced asymmetries here, which can show up in your abundances. So this is another challenge in modeling fission here. Then following this, we had collaborators, actually our chair of this session, Matt Mumpower at Los Alamos, and his collaborators at Los Alamos perform some calculations of a macroscopic microscopic treatment of fission using FRLDM to calculate yields across the chart of nuclides for neutron-rich nuclei. And what they found were yields that were particularly broad, particularly wide, both at early and late times. So what this translates into for an R process calculation is that something like this yield model is producing a much wider number of species, a much larger range of species, I should say, than something like if you just split the nucleus in half and deposit right here near the second peak. So this affects how we can interpret solar data with respect to whether or not dynamical ejecta is a dominant component. This also affects how we interpret some of these metal poor stars. You can see here the comparison with a few R process enhanced metal poor stars, where here we're producing things like silver and palladium, and here we're just not. So it's really important to model this fission. Okay, in addition to comparisons, abundance comparisons, and the effect that fission can have on that, let's talk a little bit about kilinovae. So one thing that we did a couple of years ago was to discover that californium-254, this nucleus has a half-life on the order of 60 days, and it has an incredibly high Q value. I mean, fission has something like a 200 MeV Q value. This is much higher than other Q values that we see that go into the heating, that go into kilonova calculations. So here you can see explicitly that with this being taken into account, this population of this species versus not, it's the difference between detection and non-detection for the JWST telescope. So this species, I just want to point out, is just right on the edge of where we have nuclear data right now. We don't even know for certain what's going on with its beta feeder. Is its beta feeder fissioning away before it can ever populate this species, or alpha decaying away before it can ever populate this species? There's a lot to look into up in these regions. Additionally, you can see that californium hits the sweet spot of a half-life on the order of days and having a high spontaneous fission branching ratio, but there's just a lot of unexplored territory up here. Are there others like californium, and what would be their signature?
5 minutes,
okay.
Nicole.
5 minutes. Okay, so okay, so something like this can tell you whether or not you've reached actinides. Now, if you do see something like this, you not only know you reach actinides, but you know that the local properties have to be such that you can populate these species. So these are two different models, one in which you're going around this region of very low barriers, and one in which you're going right through. And then you populate Californium heavily versus don't. We have also taken a look at more models now, a wider range of models, and we can see that your model dependence here is leading to about an order of magnitude difference in your predictions for the effective heating, bolometric luminosities, and the inferred ejecta mass once you consider these types of variations. Okay, another messenger from neutron star mergers, gamma rays from fission. I also wanted to talk about this a bit. We found that if you take a look at the gamma spectra from fission, it's very interesting. You have higher energy contributions than you do for your typical R process species that are populated at late times. So something like above 3.5 MeV is going to be completely dominated by fission. And so if you have fission here, we see as a function of energy, the type of flux that you could see. If you have fission, in this case, you are going to produce species, both these prompt and delayed from the beta decay of fission products. But if you have something that really barely reaches fissioning species, or hardly at all, you do not see this kind of signature. So it's another way to choose to see whether or not you had fission and populated actinides within neutron star mergers. Okay, post-merger disk ejecta, we heard about this a little bit earlier in the week as well, the different challenges associated with modeling this from a simulation perspective. Neutrino-driven winds versus viscously driven winds, very different results, very different predictions for the reach here. But I wanted to point out that it's mostly considered to have a higher YE range than your dynamical ejecta due to this being more processed. So you may think, oh, okay, higher YE, we don't have to worry about all of those fission inputs. But we still do have uncertainties from the nuclear physics inputs that show up here. So here I'm focusing on the R process rare earth peak. This is a moderately neutron rich condition where you can see the variations that you get from different mass models. So something like this, where you want to understand the origin of this little peak in the solar system, and you have variations based on masses, and you know some masses, is really ideal for a statistical approach where you can iterate. So what we do is exactly that. We're going to put in some masses, see what we get, and iterate to try to figure out what masses are needed to form the rare earth peak. When you do that, this is what it looks like. You can see the adjustments that we're making in the rare earth peak as we make mass adjustments to the Duflo-Zucker mass model. I want to point out, these are pretty small adjustments, actually. These are on the order of 0.5 MeV. MeV, you know, as we know, the mass of just a neutron is something like a GeV. So these are pretty small adjustments. However, they're leading to big changes in the abundances and big changes in what we would infer about the origin of the rare earth peak. Now we had collaborators go through and measure these masses independently, and we see consistency between our predictions and their measurements. However, the feature here that we found primarily responsible for the rare earth peak was this 104 feature, and this is something that excitingly will be probed by future experiment. Now we have also gone through and taken a look at distinct astrophysical outflows. So this was something that we call a hot outflow, where you have gamma N equilibrium for an extended period of time, but these things like cold outflows closer to the drip line, etc. All of these, though, are very moderately neutron rich. You can see that we get very different predictions here for the kinds of masses you need in order to form the rare earth peak. And so far, the measurements done by our collaborators are most consistent with the hot case. Now, the point of this is to be able to compare data to data. So do you find conditions that both meet the latest experimental data as well as be able to form your peak? And we could say that if all of these mass solutions just went in and formed a peak no matter what you did, what could you really say? But that is not the case for us. You can see that we took similar conditions to this hot case, tweaked the entropy a little bit, tweaked the time scale, and we're still getting a peak where there was no peak before. additionally, you put this into these distinct conditions and you get a peak, but it's way shifted relative to where it should be. So this is something that in no way our algorithm would pick out. It's just not consistent. And additionally, I just want to point out again, look at these big abundance differences that we're getting in this region with a moderately neutron-rich condition from these small mass adjustments. So in summary, I just wanted to put up that, you know, there's a lot of impact from nuclear data, and probing this nuclear data in these regions more will be really influential in understanding our observables in the future. And lastly, just kind of a cute fact, my phone reminded me that yesterday, exactly 5 years ago, was my last day at ECT STAR. I participated in the doctoral training program there, and I have a lot of good memories. So it's a real honor to give this talk here, even virtually. So thank you.
All right, thank you, Nicole. Nice talk. Any questions? Yes, Grant.
Oh, I just had a simple question. Maybe I misunderstood what you were saying. You were talking about the effects of the neutrinos and the wind, and you were saying that the material became more neutron rich when the neutrinos were driving the wind.
No, I said the opposite. I said these, yeah. I said that winds tend to be more, or sorry, okay, maybe I did say it wrong. Thank you for catching me. I'm not sure, but I meant to say that the YE gets higher, basically.
Okay.
Because it's more processed. Thank you. If I said that wrong, thanks for clarifying. This is the point where I started to panic a little bit because he said 5 minutes on me.
Nice talk, by the way.
Thanks.
I have one question, Nicole. Back on your first couple of slides when you're talking about this magic ratio of iodine to curium. So it seems to be that you know, we're favoring moderately neutron-rich conditions if we want to match solar. How do we combine this with something like an actinide boost observation like Erica has made? Is there any way to do that?
Yeah, I mean, potentially. It's interesting that Erica's studies essentially showed that something that's very neutron rich tends to make too many actinides. And this is what's happening within these calculations. We're making too much curium here. So potentially, yeah, there could be some kind of constraint that comes through that you could do like a global constraint procedure from both of these. That could be interesting. But this is, again, I'd like to point out, this is just for the last star process event that polluted our solar system. So it's not even necessarily the dominant event, but it's still interesting that we can probe these late times of enrichment.
All right, thanks. We've got about a minute more. Friedel, if you want to start getting set up, and we can field any more questions for Nicole.
I think it's too early. On my end anyway, not for the people in Europe.
All right, if there's no more questions, Nicole, thanks for a nice talk. Thanks. We'll get Friedel set up here.
This is slightly different. It's not so much, and I apologize about nuclear physics entering, but it's looking at observations and trying to find a clue whether these observations tell us something. This was done together with Khalil Farooqi, Stefan Roswog, and Karl Ludwig Kratz, and Khalil Farooqi told us everything about statistics, which is used in here. What you see at the bottom is an archive preprint which just came out. Let me see. Is an archive preprint which just came out a week ago. And if you want to see more details, you can have a look at this one. We know that we don't have a uniform solar arc process abundance pattern. There's this black dots on the right here are the Sneeden star, But then we have the Honda star with a much steeper abundance decline, and we have extremes in between. On the left, I have also given you a bunch of stars where you see here something which is called a limited R star, where we don't see observed third R process abundances, third R process peak abundances, and then we see things in between. And so the question is, do they tell us something about different events or just different amount of pollution? And we have the other thing, and that was just talked about before. We have an actinide boost stars, and if we look at the solar abundances, this LODAS gives about thorium to europium ratio of 0.42. And if you look here where this comes up, this is at the bottom here where the red stars you see. And these are predominantly what observers call R2 stars. So the limited R stars are europium over iron less than 0 to 0.3. Then there are the R1 stars for europium to iron up to 1, and the R2 stars beyond 1, and all this what we call regime 3 are enriched, and in the limited R stars we actually give 2 reasons. But so what I want to point out already at this point is these actinide boosters are not fully and completely, but dominated by R2 stars observations. So if we now, what are the possible predictions that we make in our process? For a while, the electron capture supernovae have been predicted, but these are probably very weak. I will show that at the end. Then core collapse supernovae via a new P process or a very weak R process can produce strontium, yttrium, zirconium, and maybe a little bit further, but not really a strong R process. Then the magnetorotational supernovae, initially done by Vintola, but lots of papers by Möster, Nishimura, and all have been coming on, and recently Reichert and Almudena, and they come dependent on the initial magnetic fields between a weak and possibly slightly stronger process. Then Tobias Fischer suggested just last year the quark-different confinement supernova explosions, which happen in a narrow mass range, maybe around 30, 40, 50 solar masses, and so they should be very similar. And then Siegel, Metzger, Sermon predicted collapses as a strong R process event, and we know about mergers and neutron star black hole mergers. So the question is, we have a whole bunch of things here. We have single stars, we have binary systems, and all of this is, as was talked about before, dependent, of course, on the neutrino treatment. So let me just look for a moment at statistics. First, correlations, the so-called Pearson correlation coefficient indicates whether you have between two observables a linear relationship. And up on the top left, a nice linear relationship gives a correlation of 1. If you get more and more scatter, it goes down to 0. If it has a negative trend, it will be negative. But the nice thing is, whenever it's linear, independent of the slope, if the slope is positive, it's +1. If it's negative, it's -1. If it's straight, it's 0. And all these big scatters, 0. Okay, now let's look how galactic evolution came about. There has been discussion a while ago. What are the lowest metallicity stars which we can expect? And if you have a supernova with 0.1 solar masses of iron ejected and take a set of Taylor blast wave in the typical interstellar medium, you pollute about 5 × 10⁴ solar masses. And if you then in this remnant calculate the iron over hydrogen, it's about -2.7. Or that is Ryan took 0.2 solar masses, he got minus 2.7. If you take 0.1, it's about minus 3. So that came to the conclusion whenever you have stars which have minus 2.5 or less, they are probably only polluted by one event. We will take this as a hypothesis at the moment. Of course, maybe not the next star is really produced out of the remnant, but maybe you have only 10 or 1% pollution. We will see this. And there is another point. If we look at one event which was only polluting the interstellar medium to form a new star, then we would linear find, when you have very similar events of that type, you would always find the same relation between two elements for the same type of event. So that would be a nice relation. This would be in the early galaxy where you have only pollution by one event. If you have, as a function of time, many events and mixing and whatever, you might also find the correlation. But you see this here, if you look at europium over iron in the range of between -2 and -1, then the europium to iron ratio becomes kind of constant, and that would be like a linear correlation. But this is because you have many events overlapping, and if you have many iron contributing supernovae and many neutron star mergers doing europium, you get a constant ratio, but it's a spurious correlation. It doesn't mean that in the same event you had europium and iron produced in this ratio. But if you look at very low metallicities, then where we see the large scatter of more than 2 orders of magnitude, this could give us a clue that you look at one event. There is an interesting point: is this large scatter telling us we have always the same kind of event, but contributing to different amounts to the next star formation, or do we have different types of events? And if you look on the right side of the screen, you see that in these limited R stars, that the strontium to europium is much higher. So this gives kind of a clue that maybe these limited R stars really come from a different kind of event than the R1 and R2 stars. Let me go to let me have a look at these kind of correlations. So we look at the Saga and GINA database, take all the stars with the europium over iron and look at correlations. And we see that we have at very low europium over iron, almost a correlation of almost a correlation of 1, so that this is a constant ratio. Then if what we call regime 2, we have still a pretty good correlation of 0.8, but not that good, so it's more scatter. And then if we go to the higher ratios, the Pearson correlations vanish completely, so that means europium and iron have nothing to do with each other. The so-called Spearman correlation is a bit milder measure, but what it also says, when these two differ, then we really have a different correlation pattern. So we come out of this point, we might have a category 1 type of event where europium and iron come together and almost very nicely correlated. We have maybe a category 2 type of event where they're still pretty well correlated, but with some scatter. And then we have these regime 3, where we must have events which probably where the europium and iron really don't go together. Let me come with something else, a so-called cluster analysis. You can read this all in the appendix of our 42-page paper. Essentially, it's a statistical technique to tell you whether certain behaviors are similar. But what we use is the Kmeans clustering. So we look for 3 and 7 clusters, for example. If you take 3 clusters, You see here where already you have an averaging of many events and a kind of almost constant europium to iron ratio, but a spurious correlation because it's not by co-production in one event, but just because of the mixture. And here the type 1a supernova come in, so this is a different kind of thing. But if we go at the very low metallicities with this high scatter, this is really an area which behaves differently. This is what we call here this cluster 2 yellow. But if we take a 7 cluster approach, we see that this area where you have already a lot of mixing is just spread into a number of different clusters. But then we have this interesting point, which is almost identical with what observers call limited R, R1, and R2 stars. So the question is, do they really tell us that there are different types of events? And let me give you another thing, the so-called rank test. If you take a random number generator to generate numbers, and then if you have them at the end, you line them up in a sequence of increasing numbers. And you give the increasing numbers just an integer number, and this is the rank. And if you do this with a random number generator, you get a linear behavior. This variable as a function of rank is linear. If you would add 2 identical random number generators, you would just have at each point twice the amount. You would still have a linear, but with a higher slope. But if you add 2 different random number generators, you get this different behavior, the deviation from linear, and how big the deviation is at the low and the high end depends whether one of the random number generators has lots of numbers at the low or on the high end. And so we use this also for looking at element abundances as a function of their rank. Just looking at correlations, nickel over iron, you see very good correlation. This seems to be coming together, and we know that comes from explosive silicon burning. And only for the higher nickel ratios, there's a little bit of a deviation, but still a very nice correlation. If you look at iron in the rank test, we see that it is almost linear. So iron is always coming, whether it's one type of event or one type of condition, but it's always coming from explosive silicon burning in very, very similar conditions. If you look at zinc over iron, here the plot as a function of metallicity, and here the correlation, you see that you find initially quite good correlations for the low numbers, but at the higher numbers, maybe different things come in, and this is there where at very low metallicities, the zinc over iron is going up, and maybe hypernovae and very massive stars are coming in. Let's now look at europium. I mentioned initially this regime 1, regime 2, and in regime 1, what we said, this is probably category 1 of type of events contributing, we get a very nice linear relation as a function of rank. No, we get a nice linear correlation as abundance, but the iron over europium seems to be constant. If we do this as a function of rank, it's also still quite linear. But if we include, for example, if we go to higher europium over iron ratios, we get this deviation. And if you include R2 and R1 and R2 stars, you get this very steep up. That means with at least with this R1 and R2 stars, there's a completely different production mechanism for europium coming in.
5 minutes.
Let's have a look at thorium. Thorium on the right plot, you see has a very similar scatter as europium over iron. It is just you have rarer observations. But what you also see is that you see thorium abundances observed above about 0 for europium over iron. So if we say limited R stars are the ones which do not produce the third R process peak or actinides, then we should make the division between limited R and R enriched stars around europium over iron around 0. And now let's ask the question about actinide boost. If you look at europium over thorium, we have a beautiful correlation if we take all the actinide boost stars, and we have still a good correlation, but a slight difference. We take the actinide normal stars. If we would plot this just the other way around, the actinide normal would be well correlated, and then the boost is slight variation, but it just means we see this split. And if you look on the right, you see the ratio between europium abundances and thorium abundances. The actinide normal stars are the red ones. We see an almost linear relation, but a smaller slope, and the actinide boost, a linear relation with a higher slope. So we would call these are category 3 events, which produce the R-enriched stars, but whether it's actinized boost or not, we call them category 3A and 3B events. And there is another interesting point. If you plot thorium as a function of rank, then you see over all stars, that means R1 and R2 stars, you see this slope as a function of rank. It tells you there must be a superposition of two sources. If we plot R1 and R2 separately on the bottom, you see a nice linear relation. So what it kind of says is that there are two different events which have linear relations, but if you put them together, you see you really see it's a superposition. So that means R1 and R2 stars are dominated by two different kinds of events. If we do the same thing for europium, for R1 and R2 stars, we don't see the same behavior. And the reason is there's another superposition. Europium is also produced from these category 1 and 2 events, which produce limited R stars, and these events also produce europium and pollute also the R1 and R2 events. And this is now an attempt to put this all together in a speculated, suggested category scheme. We have the regular core collapse supernovae maybe with a new P process and a very weak R process. We see that they essentially always produce trans iron-like elements like strontium, yttrium, zirconium, and maybe a little bit heavier. We see in these recent predictions by Fisher and that we have quark deconfinement supernovae which produce iron and a weak R process with europium, but not too low YE. Then we have this magnetorotational supernovae with producing iron, but weak to maybe stronger R process depending on the initial magnetic fields. We have collapsars, which according to Siegel and Metzger and others produce a strong R process. And one of the interesting points is that they predict the YE in the tori ejecta of about 1.12, 0.14. This lies just in the bracket between 0.1 and 1.5, which Holmbeck and Eichler and Wu have predicted, where you just have the best actinide boost, because if you are even more neutron rich, you have too much fission cycling, the heavy stuff is depleted again. If you are below, you don't get up to the actinides, to the maximum actinide boost you get in YE, and these ratios. So collapsars and everything which produces fast black hole accretion thorium might produce this actinide boost, and we call this category 3B events. And the regular neutron star mergers do the regular R process, R enriched, what we call category 3A events. And if we take models, okay, we have to rely on model predictions. We look at element ratios, strontium over europium, strontium over iron, europium over iron, and we look at the values in the observational regime 1 and 2, and we look at electron capture supernovae, 2 models of MHD supernovae, and 1 model of the quark deconfinement supernovae. We see that the strontium to europium can be almost matched by all models except for the electron capture supernovae. But in order to reproduce the strontium over iron and europium over iron, it seems that we need to mix in additional iron. And our explanation would be that if you are at -3 and maybe the first supernovae actually started at -5 or -4, you had to already mix in about 10 regular MHD supernovae, which end up as magnetized with a weak R process, and then you could get these figures consistently. And if you go into the category 3 events, neutron star mergers and collapsars, in order, so the europium over iron, in order to put, we know that they make an actinide boost, but the europium over iron, you can also only reproduce if you have about 100 or more supernovae or 120 supernovae, which produce the iron in addition to the europium from these type of events. So this, if you do this, this comes also consistently out with the correlation pattern showing at the bottom. And finally, I want to conclude with an observational plot showing iron over hydrogen in comparison to europium over hydrogen. And what you see on the bottom left in different colors are limited R, R1 and R2 stars. And there's a new one marked as yellow, which just came out in a Nature paper last week by Young and collaborators. The most metal poor R2 star. If you look at strontium over iron color coded, you see that these limited R stars all are supersolar with strontium over europium. If you look at the thorium to europium color coded, you see that most of the R2 stars have a supersolar thorium to europium ratio and the upper end of the R1 stars. And another interesting point is if you look at barium over europium, you actually see something even at these low metallicities like an S process enhancement. And we know of the typical S process with low and intermediate mass stars starts only at metallicities about -0.5 to -2. But this is an indication these very massive spin stars with shear, which due to shear mixing make primary nitrogen and neon 22 can have an S process as well. And this would go in the other direction, that these R2 stars are polluted by very massive stars with these S process additions. But at the same time doing this actinide boost due to the accretion-Thorium outflow. So this is maybe a bit speculative and should be tested with modeling, and whether the models we compared with are the best ones or have to be improved is another question. But it's just an idea whether by data mining of these low metallicity stars, we can learn something about the contributions from different types of R process events, whether it's all neutron star mergers or collapsars or also weak R process producing things. So that is my conclusion at the end.
Hey, thank you, Friedel. This is really great analysis. It's nice to see statistics applied to this problem. Chris has a question.
It's probably a bit speculative and should be tested, but it's kind of a suggestion to look at these things in more detail.
Yeah, I mean, well, just from a statistics perspective, I mean, one thing you could look at, in the future is this: if you have some model distribution of these stars, you could do something like a Kolmogorov-Smirnov test.
Yeah,
that would be interesting. Okay, Chris had his hand up, and then we have Erica, and we should also move on to the next speaker just after those two questions. Chris, take it away.
So hopefully mine's quick. I really like this kind of study. One of the things that I like seeing trends, but I also, I hope that we can understand the scatter, how much of the scatter is observational and how much is real, because the scatter sometimes is a better constraint on the models than even, seeing the trend, that's fine, but understanding the level of scatter we can get can really help us constrain the model. So I'm hoping that there's work being done to understand what's causing this variation, and how much of the variation is real. And I was hoping you could comment on that.
Of course, this is a Saga and Gina base, and this is not a consistent analysis. This is just put everything together. So there's probably the scatter is somewhat exaggerated in comparison to if you would have only one line of observational study. But then there is another question. So my feeling until maybe a year ago was the big scatter just tells us it's rare events. And then it depends whether this area, whether the one new star was born, was polluted heavily or only a little bit, maybe by 1% or 10% or whatever, or 1 per mil of a nearby merger or whatever. So this produces the big scatter if you have rare events. What came up at this point is that some of the scatter could also come from having different kind of events. And that is what came out of this, or which this analysis brought us to thinking that maybe, the collapsars always produce a lot of europium, neutron star mergers produce also a lot, but smaller amounts. And these weak R process events produce even smaller amounts of europium. Is it also that this scatter is not only due to rare events with different amounts of pollution of pockets in the interstellar medium, or is it only also that we see pattern of different types of events?
Yeah, and I would say that even within a given event, say pick your thing, they should predict a range. Like supernova would predict a range of what it's producing depending on the qualities of the collapsing star. Same with neutron star mergers, depending on the components. And so, yes. I'll give the analogy. Initially, for compact remnant masses, there was a paper that said they're all delta functions. They all have this mass. And it was because the pulsar systems that were observed all had one mass. And we had no way to explain that in theory. So we kept on saying that cannot be the right answer. And then we started to get better observations, and we see there's a range of neutron star masses. And that actually helps us understand our theory way better than that delta function did. And I think within each of these sources, we're getting to the point. I think the first step is what you're doing, which is saying there's clearly different sources. Then within each source, there should be a range of results, and we should be able to see that in the data. And if we can, that would be excellent.
Yeah, I fully agree. And I take any criticism. This is kind of a brainchild, and there might be spukes in it and logical glitches, but we just wanted to present it to the public.
Okay, Friedel, could you stop sharing so we can get Taka set up? Yeah. And then Erica, while we're doing that transition, can you ask your question really quick?
Yeah, Friedel, great talk. That was really interesting work. This type of statistics on stars, I think, is something that really needs to be done. So I'm really happy to see that it is being done. I just have a couple of comments just to consider, moving forward when you're doing this type of analysis. And that is, first of all, with the limited R stars, they're not just defined by their low europium. They're most notably defined by their high strontium to barium. So just throwing that out there. I don't know if that was something you considered.
This is actually what I showed on I think the second slide. This very large strontium to europium ratio for all the limited R stars. And this is actually one of the conclusions why we thought this might be a different source. This is not just a variation in the same, this might be really a different source.
Oh, absolutely. Yeah, no, I'm thinking back to the Kmeans clustering plot. I just wanted to make sure that when the limited R stars were in there, that was something that was
yes. On the right side of this plot where I showed the Kmeans clustering, you showed actually the limited R, the R1 and the R2 stars showed up as different clusters. And that actually was nice. You see, initially I thought observers just brought this up as a kind of, I don't know, category or book making. But when one really sees that there's different behavior in these different clusters, and this is another indication that probably we have different sources contributing there.
Yeah, absolutely. And actually, we also used a Kmeans clustering algorithm to redefine that separation between R1 and R2, and we pushed it lower to be 0.7 instead of 1. But with the limited R stars in that group, I just kind of want to caution that, yes, it is really, really great that you could also pull that out statistically, that limited R group, but not all stars in that group will be limited R. That's just all I wanted to point out there. With the actinide boost stars too, and seeing how they are more frequent for high europium enrichment. And so, you know, a higher fraction of R2 stars happen to be actinide boost. Yeah, that's also, there's some observational bias behind that, because it's just at the stars that are most enhanced in our process elements, it's easier to see thorium. So it's just easier to measure. There's no reason to believe, I think, that thorium is not present in things like the limited R stars. It's just something that we can't really see right now, because it just isn't abundant enough to be able to detect.
Actually, if you look in the quark deconfinement supernova by Fisher et al., which shows a very weak R process, quite a number of about a factor, I think a factor of 10,000 down, you have also thorium there. So I think all of these produce something. The question is whether it comes above the observational limits.
Exactly. Yeah. Yeah. So I personally believe that thorium, or the actinide boost frequency is, I have no reason to believe it does have a trend with europium to iron. I think, why not? Why can't it be consistent amongst all of them? And sorry, I know I'm taking a lot of time, but I just wanted to kind of answer or comment on Chris's question too. Yeah, I agree that variations of the same site could also account for some of the variations we're seeing. We wrote a paper on this that was published this year, where we saw that neutron star mergers, just neutron star mergers, can reproduce this entire variation of europium to iron and even thorium to europium, or sorry, not europium to iron, I'm sorry about that. A lot of variation of the limited R process elements to the lanthanides, and then the actinides to lanthanides. So I just wanted to mention that as well, that we are saying that we can produce this wide variation even within the same site. Doesn't mean that it's that one site that can account for everything, but it just makes the picture that much more complicated. It just increases our degeneracies with what sites are these sources. So sorry, I just wanted to make those comments.
It's a YE between 0.1 and 0.15, and wherever you can get it, you will get a lot of actinides. And the question is in which environment you have these kind of conditions. You showed that in your paper. This is where I saw it the first time.
Thank you. Anyway, that's it. I'm done. Sorry for taking so much time.
Oh, it's a great discussion. Thanks, everybody. All right, Taka, can you start sharing your screen?
Yes.
Okay, take us away.
Okay, yes. Okay. Thank you, organizer. It is really my pleasure to talk about the laws of nuclear physics, especially fission in collapsar, merger, and supernova R process. And today we have already very beautiful talk about the fission. So complementary, we will talk, first of all, after introduction, we will discuss galactic chemical evolution of our process elements by taking account of binary neutron star merger, supernova, and collapsar jet. And after that, we will discuss the laws of nuclear physics, especially fission, not as a physical viewpoint, but from nuclear physics viewpoint. And lastly, we summarize my talk. So this is a sketch of cosmic and galactic evolution and the origin of elements. Needless to say, in order to study the origin of elements, we should take account of the cosmic evolution, because our process elements are undoubtedly coming from several different astrophysical sites. Massive stars, one candidate, and the neutron star mergers, the second candidate, and many more, as Friedel has discussed. But the point is, although there are many possible candidates of our process contributor, when in the cosmic history, they make a contribution to enrich the our process element in the interstellar medium. So in order to answer this question, we should go to the galactic chemical evolution. Today's talk will be given to 3 different subjects. Of course, this workshop is for discussing the nuclear physics associated with the neutron star mergers. And also, we cannot ignore the supernova, single star explosive nucleosynthesis. But in addition, recently, we have some of a discussion of important contribution coming from collapsar jet. It is the single massive star evolution, but the remnant is black hole. And the Ziegler et al. Proposed that the collapsar as a superluminous hypernova, but collapsar is different. It is a failed supernova. So anyhow, we will discuss the nuclear physics and astrophysics of galactic chemical evolution among these 3 candidates, by the neutron star, supernova, and collapsar jet. Let us start our discussion from the first subject of cosmic and galactic chemical evolution. It is, of course, to be considered the cycle of star birth, massive star evolution, explosion, ejection to enrich the interstellar medium by our process elements. In order to consider the supernova or collapsar event rate, which is a single massive star collapse and explosion, it is straightforward. Depending on the mass at birth, lifetime is different. Therefore, we take account of lifetime delay before the explosion. However, when we take account of the binary mergers, it is more complicated. From a star-forming cloud, there are many masses of stars were born. Depending on the mass, the lifetime is different. However, complication starts. They should leave the neutron star, if this is a neutron star merger, and then kinematical conditions of a distance, and also the mass ratios or the frequency, and also, in addition, the delay time due to the very slow gravitational radiation until they merge. But we take account of all these both kinematical and chemical ingredients into our galactic chemical evolution models. And as for the coalescence times delay, we take account of at best the observed double pulsar, binary pulsar observations. Here we show the observed orbital eccentricity and orbital period. 14 binary pulsars were observed. And by applying the general relativity, we can estimate how long it will take until they will merge. The important point is the lowest limit among the observation is 100 mega-year. This is a delay, cosmological timescale. And some of the binaries will merge about the 10 trillion years in the future. But anyhow, there is some frequency of the timescale, so we take account of all these contributions in a previous formula of galactic chemical evolution of binaries. Okay, now the first application is dwarf spheroidal galaxies. Here we show just a neutron star merger contributions to the europium abundance as a function of metallicity. If we take the merging delay time very short, unrealistically short, 0.37 mega-year, some of faint massive dwarf spheroidal galaxies are explained. However, it is too much. It is unrealistic. 100 mega-year is a standard observed lower limit. So near the solar neighborhood, it misses the prediction or the observational fact of chemical evolution of our process element. It is more clear if we show some of the numerical calculation by artificially switching on the neutron star merger contribution from 0 to 100%. Therefore, 0% of neutron star merger correspond to the cluster plus core collapse supernova contribution 100. So here, obviously, we would say that the europium abundance, typical our process element, are missed only by neutron star merger contributions because of the time delay. And it has already been pointed out by Benoit Cote that near the solar neighbor fault or higher meteoricities, only neutron star merger contribution misses the general trend of our process element galactic chemical evolution. Okay, now the point is what kind of event rate we should assume in order to study the each contribution from neutron-driven wind supernova, MHD jet supernova, binary neutron star mergers, and collapses. So at best, we take account of observed event rate. The ordinary neutron star leaving supernova, we know the frequency. Once or twice per century per BQA was observed by aluminum-26 in a galactic chemical radioactivity in integral observations. And MHD jet is probably a few percent of this total supernova. And the binary neutron star mergers, probably it is the central engine of a short duration gamma ray burst. So we will use the observed frequency event rate of short duration gamma ray burst. However, there are many uncertainties in observations. Why GW170817 is so faint? Is it probably due to the jet inclination or beaming, or some of observational threshold? Anyhow, if it is true by one event of GW170817, it is enough for us to assume at the moment the short GRB is event rate for binary neutron star mergers. But the collapsers, we should be careful about this. Our collapser is, of course, a faint supernova, failed supernova. It is not luminous. But a few years ago, Ziegler pointed out their collapser is a hypernova, long gamma ray burst. Event rate is applied, and it is a kind of luminous supernova. And it could be possible, but our collapser is not a superluminous supernova, long duration gamma ray burst. So we don't know absolutely the event rate. However, collapser is a kind of extended higher mass N over rotational magnetic driven supernova. So we assume the same frequency of MHD supernova, MHD jet supernova. Okay, having all these, we can do our simulations of galactic chemical evolution. Here we will show the movies from the early galaxy until the solar system. In the early galaxy was dominated by supernova and collapsers. But as the time passes by, neutron star merger start contribution because of a time delay. The point is, each contribution depends on cosmic time. However, at the moment of a solar system, they contribute almost equally. Of course, 10% or 9%, it is different, but all of them can, in principle, contribute. What we have now solved is this. In the early galaxy, collapse and supernova dominates, and the time passes by, meteoricity increases, and neutron star merger start contribution. Then in the present solar system, they all contribute. However, if we take account of only element abundance contributions, although the mass distribution, A distribution is this much, especially a collapser contributes to have a zigzag contribution in the early galaxy, but the element abundance is almost the same. So our first quest to astronomer is, please observe the event rate accurately, and secondly, separate isotopes and mass distributions, even in 1 or 2 isotopes in the metal heavy nuclear regions. Okay, now, having all this galactic chemical evolution, we will study now the nuclear physics. The second part of the purpose to discuss is to elucidate the role of fission, weak rates, strong magnetic field effect in 3 different sites equally. Let us start our discussion from fission. In order to discuss a fission from nuclear physics, we take account of all beta decay, neutron capture, and so on, because mass is very important. So from now on, we compare with the Japanese-made mass formula, KTUY, which describes not only mass, fission barrier, Q beta, and others. And we compare with benchmark study of FRDM model. But as for the beta decay rate, our model described the newly discovered neutron-rich radioactive nuclei in our process regions. Okay, now let us briefly explain what kind of nuclear model of fission we adopted. First of all, we parameterize the shape. Parameterization is to be done by introducing a corrective coordinate as a generator coordinate, elongation, deformation of each fragment, and also mass asymmetry. Having assumed this, we can estimate the free energy surface to indicate symmetric or asymmetric fission could occur on each of the isotopes in the neutron-rich actinide. Looking at the potential depths at the fission barrier near the scission point, for example, here, if we assume the symmetric fission, the fission height is here. But if we assume the asymmetric fission, the saddle point is here. So we compare this height. These are very critical, so-called fission barrier. If the symmetric fission depth of a fission barrier potential is lower, probably fragment would be symmetric. But it depends on isomer. It depends on isotopes. So we take account of all these possibilities. But this is only a static property. So in our collaborators model, we carried out a 4-dimensional Langevin equation models to describe not only the static properties of fission fragment distribution, but also the dynamics of scission, fission, and fragment. So when we carry out the 4D Langevin models, Thorium 256, the double peak fission fragment distribution is very well described. But if the symmetric barrier is lower than the asymmetric barrier of a scission point, symmetric fission will come out. We take account of all these contributions coming from the dynamical fission calculations. Okay, this model can describe not only the fission fragment distribution, but the trimodal models or the kinetics very well. So it is one of the successful model of fission dynamics and fission fragment distributions. Okay, now we will try to apply this to 3 different sites of our process. Now, fission is in generally 3 peaks. So we parameterize these peaks extrapolated from the measured fission fragment distributions. It is interesting. It's a fission comes to the fissile region of symmetric fission, it will come to split around the peak of the secondary process elements. But if it is coming to the fissile regions of binary fragment fissions, it doesn't describe the single peak of the secondary process, our process peak element. So we will demonstrate this in neutron star merger, our process. In the earlier time, the fission reaches to the symmetric fission region. So symmetric fission dominates in the earlier time. However, as the time passes by, neutron is exhausted and triple or double fission dominates. We take account of all these contributions for all possible fissile regions. Now we will apply to the 3 different astrophysical sites. First, supernova, neutron dimming wind, MHD jet. And as you have already known, this ordinary neutron star leaving supernova cannot contribute much about actinoid production. Therefore, fission recycling does not affect very much the R process abundance. Therefore, we will move to the neutron star mergers. Neutron star mergers has a much more neutron-rich conditions by 5 or 10 orders of magnitude compared with the MHD jet supernova. Therefore, fission region is easily reached. And here we show the final result. If we adopt our very natural fission models, fission fragment models, including both asymmetric and symmetric, the second peak is washed out. But however, if we constrain ourselves artificially to only the symmetric fission fragment distributions, second peak will come out. So in this way, fission nuclear physics, especially the dynamics, not only the fission fragment distribution, plays a very, very important role. So we should study both experimentally and theoretically the fission. And then we will discuss the consequence impact on the R processing neutron star mergers. Okay, last object is collapsar jet. Collapsar jet has, for the first time, being discussed by McFadden and Woolsey and Nagataki. But we independently in our group extended our calculation in the 2D hydrodynamic models. This model takes account of failed supernova, namely the central object remnant is black hole, and black hole and high temperature accretion disk is formed. And the MHD effect and the neutron heating trigger the energetic jet. And here we should pay attention to the fact that this is a failed supernova, not a superluminous supernova, namely not a hypernova as assumed by Ziegler. So we have used our own collapsar model. The characteristic of collapsar model in the modeling of our process is the following. We first set up 20,000 tracer particles of MHD neutrino pair heating hydrodynamics in 2D. And among them, after simulation, we found that 1,289 trajectories are ejected, therefore contribute to the alpha process enrichment into the space with positive energy. And very interestingly, entropy per baryon is from 100 over 10,000, very high entropy, keeping the very low YE, namely the very neutron rich. The point is this: the surviving ejected accretion disk materials is very neutron rich at earlier time, and then because of the rotation, it will get out of along the polar jet directions. This is very, very neutron rich. So it is a condition ideal for our process. Okay, now we apply our model to the collapsar jet R process. First, we will discuss the importance of fission. Above panels show the cases without fission. This is the nuclear chart. This is a nuclear abundance evolution in time. The lower one is the case with including fission. You see, without fission, the actinide elements are accumulated, of course. However, including fissions, this will fission recycle to enrich the R process elements in the heavier nuclear regions. So the difference is so obviously big. And here we show our analysis of the fission roles, asymmetric or symmetric. The upper panel is symmetric case. The lower panel is both including symmetric and asymmetric. So the difference is obvious. Even the R process, Layer and Hill are different from each other between these two fission models. And in addition, we also discussed the weak rates dependence. In the blue curves is for the case of using the Gina reactive, which is based on the Miller mass formula and beta decay and many others. This take account of nuclear structure properties very well, mass formula very well, but no temperature dependence. But Alcornes et al. Paper take account of approximate weak rate which depend on temperature, although it ignores the complicated structure formations. So both are partially okay, partially no good. But the difference is so clear. And also, in addition to this, we take account of relativistic effect because, you know, collapsar induces a very high temperature magnetized jet. So we take account of magnetic field effect. The first is relativistic Fermi screening, and the second is Landau quantization, of course. Relativistic screening should take account of both electron, positrons equally. But when the magnetic field is strong, Landau quantization should be taken into account, and we should solve self-consistently all these effects in solving the Poisson-Boltzmann equations, which comes from not nuclear physics, electron, positron effect, and also the Landau quantization effect. So the beta decay spectrum is so different by including both effects. When the magnetic field is as strong as 10 to the 15 Gauss, the lowest Landau level occupies more than 30%, but transition of beta decay is bigger than the case without magnetic field. Because of this, here we have shown the result. Compared with just a screening effect, including the inclusion of Landau quantization levels, the only lowest level of all levels, the difference is this much. We are interested in not only the general trend, but also the shift of the peak. For example, this third R+7 element here, it is shifted depending on the screening effect with or without, and also Landau quantization effect. In this way, magnetic field effect is still in the matter of theoretical nuclear physics, but astrophysics, astrophysical objects include all these magnetic field effect and nuclear physics effect, as well as astrophysical ejecta dynamics. So we should take account of all these points one by one, and finally, we should integrate. Okay, now let me summarize my talk. The early galaxy was dominated by supernova and the collapsar process. Neutron star merger has arrived later in cosmic evolution, but all these contributions are important. So we should study all these contributors. And quest for nuclear physics is to study from now on, first of all, fission, second, weak rates, finite temperature effect, and also the effect of magnetic field. So it is now very interesting to have an era of multimessenger astronomy because, you know, 4 elementary forces, including strong interaction. We have 4 messengers: neutrinos, gravitational waves, and photons, and nucleus. Integrating all these observables and integrating all these nuclear physics and astronomy, we, in the near future, would like to arrive to the true solution where the out-process elements come from. Thank you.
Okay, thank you, Taka, for that nice talk. Do we have any questions? I have one. Oh, okay, Jonah Miller. Okay, we got Jonah and Erica. Jonah, take us away.
Thanks for the very nice talk. I wanted to ask about the hydrodynamics of your collapsar jet modeling.
Yes.
Something that we, when we did our own modeling, we sort of had 2 concerns when we were thinking about the jet, and I'm curious what you think about this. One is that we didn't really trust the jet, at least the mass flux through our jet in our models, because it's an Eulerian code. And so it's baryon loaded by the artificial atmosphere we had to introduce. And the other is that we were concerned about how well that material is going to tunnel through like an infalling stellar envelope. And I don't have good answers to either of these questions, but I'm curious what you all thought about it when you were doing this modeling.
Okay, so maybe I don't say any answers, but you know, the collapsar hydrodynamics, it is very interesting, but difficult. And the reality would be 3D, general relativity, and also the accretions and microscopic physics and the microscopic physics, as you said. But at least the general trend as studied by Takiwaki, who is one of our strong collaborators in Tokyo group of supernova and MHD jet, we just try to rely on their analysis for the collapsar. I'm very sorry, just I say just my, I believe so. Of course, as you said, especially in the jet directions, the dynamics is relatively simpler because there is no centrifugal barrier, so it is easily ejected, the matter, and it is very high, so keeping the low YE, because neutrino effect is heating. However, the jet time scale is very short, therefore it keeps the neutron richness. So I think there are many points to be studied more. However, these points along the jet direction and keeping low YE and the smaller time scale relatively to the disk directions, this nature is probably okay. So, well,
yeah,
this is one.
Yeah, I mean, what you're saying makes sense. I guess what I'm more worried about is like how much mass actually comes out in the jet compared to.
It is huge. 0.1, 0.01 solar mass in one jet. Yeah,
that's assuming the jet is unimpeded, right? And that and that the model of the jet flow is actually trustworthy.
Okay,
that's what we were worried about when we were thinking about this.
I see.
But
yeah, anyhow, we'd like you to study more, you know, your professionals. But one point is, as I told you, failed supernova is a collapsar, but it is totally different from hypernova. So we should take account of this difference more clearly, or just, you know, having numerical simulations, people jump on that possibilities and the application to that process. But this also is a very difficult question, how to distinguish hypernova from collapsar and phase supernova, and what is really a superluminous supernova, and is it really the central engine of long gamma ray burst? All these should be probably studied from nuclear astrophysics. Astronomers could determine the frequency event rate of long duration gamma ray burst, but it is a huge event rate. Wow, okay, a lot of things to do. Thank you for asking.
No, thanks for your answer. That was interesting.
Okay, Erica.
I promise this one will be quick. I just wanted to address the question that for astronomers potentially reporting isotopic abundances. As you know, that's very difficult. It's only been done for a handful of elements. Recently, there's a paper by Ian Roederer et al. I can't remember if it was this year or last year, but they reported some isotopic abundances of lead, so that could be useful. But for the most part, I think it's okay to trust the solar isotopic abundances for the elements that don't have the actual measurements. So you can go ahead and use those, and then the ones that are available, like lead and europium, I think barium as well, you can use those from observations too.
Yeah, that's right. Thank you very much. But I have a collaborator, Wako Aoki, who is a main user of high dispersion spectrograph of Subaru telescope. And he was succeeded in observing barium isotope separations and the europium separation and some others in an even odd effect. So just from a theoretical viewpoint, I just do hope even one or two typical process nuclei, I hope they will identify the mass distributions. But as you said, it is always, just a desire, but reality, it will take more time or bigger telescope and much more powerful high dispersion spectrograph.
Yeah, exactly.
Someday, next generation, like Hubble Space Telescope will be launched, I hope. Well, okay. I don't answer to
okay, last question from Gabrielle.
Taka, if I understood correctly, you assume that high magnetic fields of 10 to the 15 Gauss when nuclei are present, and you assume look on the impact on beta decay. However, I have a hard time to believe that by the time the nuclei are formed, that typically you need to have low temperatures and the material is far away, the magnetic field will be so large because it has to decay at least like 1/r to the cube, because if you assume a dipole magnetic field.
Okay, yes, I have asked this question many times with our collaborators with Takiwaki, but in his simulations, toroidal magnetic field as strong as 10 to the 16 Gauss extended up to 900 kilometers. If it is leaking as a spring into the jet directions, at least this level of 10 to the 8 centimeter magnetic field is as strong as 10 to the 16 Gauss. So of course, for the cost of numerical calculations, they couldn't follow all calculations until the very later time. But from his experience, he suggested me that it will extend to almost 100 or 500 kilometers from the central black hole, keeping 10 to the 15 Gauss. Having this information from Takiwaki, we have assumed, magnetic field as strong as 10 to the 15 Gauss. So we should also listen to numerical astrophysicist answer now or in the near future. But it is a very good, important question. Thank you, Gabrielle.
Okay, thank you, Taka. Let's move on to Trevor. Trevor, you also wanted to test your mic real quick while you're setting up?
Yes. Is it coming through or no?
Yes, it is. We can hear you.
Okay, good. Yeah, okay. It's always, you never know what you're gonna get soon, I think. For this talk, I'll be talking about some work I did with Mish and Matthew Mumpower on a radioactive decay network that we had written with the specific focus for the modeling the later stages of the astrophysical process. So there's this little disclaimer that we're required to show here at LANL. So just a bit of background. So atomic nuclei via radioactive decay are one of the driving forces for observable phenomena that gets associated with ejecta from neutron star mergers and just more generally explosive astrophysics, astrophysical events, supernova and the like. And while nuclear reactions are extremely important for determining sort of how the nucleosynthesis in that ejecta proceeds, especially in the first maybe 1 to a few seconds and some latent reactions for a few more seconds beyond that. It's quickly the case that nuclear decays dominate on all longer timescales, so minutes out to days, months, years, hundreds of years, millions of years, et cetera. In particular, in a response to rapidly falling temperatures, densities, and free neutron abundances in that ejecta. And so this code that we wrote together, Jade, is specifically focused on modeling these later phases of nucleosynthesis, where it's strictly undergoing a sequence of radioactive decays. for reasons that I'll get into here in a few slides. So if we would look at a more typical treatment for this nucleosynthesis and ejecta problem, you have a system of differential equations that govern that evolution in reference to things like cross sections, densities, temperatures, and your abundances, where you have these 2-body and 3-body reaction terms appearing in your equations, in addition to a term that's linear in your abundances, particularly associated with decaying of nuclei. However, if we strip out these 2- and 3-body reactions for the moment and adjust our notation slightly, which I'll get into in just a bit, we see that, in fact, now we're linear in our individual abundances, which opens up the solution of this system of differential equations to a broader range of solvers. So just to go a bit through the notation here, we have our abundances Y. I would index a unique nuclide, so a pair of proton number or atomic number and atomic mass number. And we also had a focus on applying the problem to nuclear isomers in the same type of systems and treating those properly. So we went ahead and added an extra index, the second one. The index is the different number of long-lived nuclear states associated with each nuclide to whatever extent they're known or can be predicted. And then we have a term that expresses that a nucleus decays via a particular reaction rate, which is allowed to have some time, for instance, temperature dependency, and also an expression for the formation of nuclei via the decay of a nucleus into some other nuclei via average multiplicities via that decay. But getting back to this point that when we rephrase this problem in reference to radioactive decay alone, and the equations now being linear in those abundances, there's more, and I would argue better ways for solving these equations. So when you have these nonlinear terms, you would typically result to something like an implicit solver via discrete time stepping. Whereas these equations now can be applied or solved either exactly via the Bateman equations, though admittedly only in unique circumstances based on the decay series, their structure, some meta-analysis of the different rates that go into it that can, in some instances, cause these equations to have singularities in them. So the approach that we actually took with Jade was to apply this matrix exponential approach, which I'll get into on the next slide. But the important point being that these methods are certainly much faster than trying to apply a solver method that would be applied here. And they're probably more accurate in most cases as well. So just to revisit this idea about the matrix exponential as a solution to these equations, we would begin by constructing a matrix that embodies all of the decay rates and the branching ratios and multiplicities located in this equation here, where now M and N are used to index rows and columns. So each M and each N reference a unique pair of I and J. So a bit of a change in notation from here to here. And the point being, though, that ultimately, once you construct this matrix, you can apply the matrix to a vector containing the abundances using the same indices. And for arbitrary abundance vectors, it'll return to you what your time derivative is for those same abundances. And if we just quickly recall the exponential of a matrix defined in reference to this power series, then the solution of abundances at a time t that's later than some initial time t0 is given by the exponential of this matrix here where you integrate over this time step out element-wise all the time dependencies for that matrix, and then in turn exponentiate the integral there. So on the one hand, this allows us to phrase our solution to the problem very easily. What you get in return, though, is the fact that matrix exponentials are in fact very difficult to solve in like a numerically stable way that's applicable to all the different use cases that there are for exponentiating a matrix. Some of the ones that would tend to work well for these particular applications, especially to the extent that they get applied to the sort of qualitatively similar reactor burnup equations, are, for instance, Krylov subspace methods. You can just truncate this expression here to finite order. You have a Chebyshev rational approximation method that works quite well. But the one that we went with in developing the JADE code was this fairly recent development of this scaling and squaring technique that seemed to work quite well for our particular application. And I'll get into a little bit of benchmarking here in a slide or two. So the standard work or procedure algorithm for this problem is to evaluate or to time evolve time step nuclear abundances from an initial state to a final state over a series of enumerated time steps via repeated evaluation of the exponential of this matrix here, which if you constrain your time steps to be small, such that lambda doesn't vary so much over your ti to ti plus 1, you can just approximate it as a scalar times your matrix with the time dependency evaluated at this time step here. So in particular, we have two constraints here that we're trying to really hit on. One being that we want our solutions to be numerically accurate given the technique we're employing to evaluate this matrix exponential numerically. And we also want to be able to capture the time evolution, the potential time evolution of this matrix here accurately as well. So for this first consideration here, we're trying to constrain our time steps so that the product of the size of the time step with some notion of norm of this matrix here is less than a constant. I believe in our code, we set the constant to 100. It seems to work well. It could probably be much larger given this scaling and squaring technique, but it's a criteria that's, again, been used in similar problems when applied to reactor burnup. And then the second criteria we have is just that, again, that lambda, this matrix here, is approximately constant over our time step as well. So in particular, this time dependence was important for us to implement in the JADE code because we needed to reliably model, among other effects, these thermally mediated transition rates between nuclear states that Wendell presented at some length on this past Tuesday. So I'll get into a bit more about both of these considerations here on the next slides. For this first example, we prepared a system that we could solve with JADE, for which we could also compare to an exact solution obtained via the Bateman equations. And in particular, the way this worked was we initiated some initial abundance on the A equals 130 isobar for some short-lived neutron-rich isotope, allowed it to decay back, and we just plotted here with the blue lines our abundances simulated with JADE, and we compared at a series of points along those same curves with the exact solution, and we see that we get a good agreement with our exact solution across 9 orders of magnitude. So this is from milliseconds to a few days, and also across nearly 14 orders of magnitude in abundance. So as far as concerns the numerical stability and numerical accuracy of this approach, we feel we're in a very good spot with this code. And then, as mentioned, we had a particular focus on getting these time-dependent rates. So more specifically, if you have some R process ejecta, it's very hot. And as Wendell showed earlier, you can have these thermally mediated transitions between ground states, isomeric states, via direct transition, as well as via feeding from beta decay, where you have some initial equilibrium state, you freeze out at a temperature, and then you have subsequent decay using sort of the natural or zero temperature limit of the decay rates. And we did extensive benchmarking to confirm that all these effects were being captured effectively and appropriately. And so just to kind of recall back to his work doing all of this with this new capability in this code, we were able to isolate this huge swath of known isomers that were furthermore isolated and filtered out to identify which ones were probably or most likely to be influential in some capacity or another in the later time of the decay of this ejecta in like an R process-like environment. So in a separate work and sort of the work that was meant to describe the code and some first applications of it, we started by taking jade and preparing an initial abundance along the 1 neutron drip line, where we constrained it to reproduce the solar isotopic abundances at the conclusion of the decay. So once everything is finally stable, confirming that or constraining it to reproduce those exactly. And so here we just plot as sort of a first example of the code that yes, in fact, we can plot, calculate these abundances 1 second, 1 minute after we start the system, and then 1 hour after decay. And in particular, I'll note that, on very short time scales where your time is sort of short or relatively similar to the half-lives of the nuclei that were initially populated, you have this broad swath of nuclei that are populated. So it's very broadly dispersed. But as you move towards later times, it becomes more narrowly focused on a much smaller range of nuclei being populated. And then certainly by an hour now, we're just a few nucleons away from stability in all cases. And so this was an effect we were trying to explore further. So how does this sort of effect influence the nucleosynthesis that we're predicting? And it led us to this idea of isochronic evolution for these types of problems. And so just to take a step back to kind of make this point.
5 minutes, Trevor.
5 minutes? Okay. So as nuclei are decaying from shorter lived to longer lived species, you have this tendency to populate nuclei with the half-life that's proportional to the time you're at in your radioactive decay, mostly because of the steep gradient from very short-lived to very long-lived nuclei, where this dispersion of these many short-lived nuclei kind of wash out, and then you end up in a smaller handful of nuclei towards the end that are populated. And so just to try to illustrate this point, we looked at two systems, one that was situated on the drip line, one that was, a fairly large number of neutrons closer to stability, but on the same decay series. And we plot separately their abundances as a function of time for each of those evolutions. And we see at early times, yes, of course, there's this dispersion, this disagreement that lies between the evolution of the abundances. But as you move towards longer and longer times, and certainly by a second for this particular example, you're in good agreement between the two initial states, which is to say, it didn't actually matter whether you started on the drip line or that many neutrons closer to stability, because after a second, their evolution of their abundances are effectively the same. to all considerations. So just to look at this more concretely for something more like a full R process, we did 1 million Jade calculations. So coming back to this numerical efficiency that we have with Jade, where the initial conditions were randomly varied to between nuclei with half-life shorter than a second, and then the drip line, but where in all cases they're constrained to reproduce the same final abundances. And as before I said, around 1 second, here we plot the sort of the relative error across the million samples, and it's proportional to the abundance itself. It's 100%. It's very uncertain across the broad range of the charged nuclides. However, even by the time you've reached 1 minute and certainly by an hour, this metric's dropping to 0, which is to say, despite this massive range and these initial conditions that we prepared across this fairly enormous region in the charged nuclides for the initial abundances, by 1 hour for all practical purposes, they're in complete agreement. And just to put numbers on this, by 15 minutes, you're looking at abundance deviations from like the upper bound and the lower bound of this range for each nucleus to within 1%, and all abundances to within an agreement of 10 to the minus 8. And so we just plot the upper bound of both of these, sort of the nucleus that maximizes the uncertainty and abundance across the million samples that we prepared, and then the same but for the relative error. And we see that, certainly by a day, these uncertainties are negligible, and for astrophysical purposes, modeling purposes, even at 1/100th of a day or about 15 minutes, they're all but negligible in both of these metrics. So just quickly, I'll running out of time. We'll just discuss that, of course, now that we're able to model abundances as a function of time, both with Jade assuming some initial condition, or even by applying this isochronic idea where you fix the final isotopic abundances. These can be coupled as an input to the modeling of various observables associated with our process Ejecta. Of course, there's several caveats there, one being that you still need temperatures, densities, and other quantities to model things like light curves. And also this analysis that we present becomes considerably more complicated due to degeneracies that are introduced once you start to populate the heaviest nuclei that are going to fission or end up on alpha decay series. But just in general, if you take this idea and you go with it, on the timescales considered, for sort of observationally relevant timescales for these events, the nuclei that are populated already have a wealth of experimental data that's known. Most of their, or at least the majority of those properties are measured, where most importantly for this analysis would probably be half-lives, which in almost all cases, even after a minute, the nuclei are populated tend to have, with a few exceptions. And so just to summarize this point, we're by using this approach, this isochronic analysis approach, we're effectively exchanging uncertainties in the theory of the heavy neutron-rich nuclei during the initial stages of nucleosynthesis for basically the inability to know what the nucleosynthesis yields are for a particular event. Or I'd say as far as just modeling abundances versus time goes, not with respect to observables so specifically, probably one of the last remaining uncertainties for many of these nuclei will be tamping down these nuclear isomers, which can have effects like capturing an abundance and making it very long-lived, whereas the ground state might be short-lived, or vice versa, which again was sort of an effect that was initially explored by Wendelmish in this work, and sort of as a motivating factor for doing future experiments in these isomers. I think I'm probably close to out of time, so I'll just leave these slides up, but say thanks to everyone and take questions.
Okay, thank you, Trevor. It looks like Jolie has her hand up.
Nice talk. So as we know, in an R-process event, the number of neutrons does not go to zero from some very large number like 10 to the 22 per square centimeter per second. And so the question is, an example I talked about earlier this week was Tin 130, which has a ground state, which is 3.7 minutes, and a 7- isomer, which is 1.7 minutes. And so you could still have neutron capture at relatively late times, 1 minute, that could affect your mass 130 abundances, because as soon as you have a neutron capture, you change your mass by 1 unit. So do you have a sense of how long after an event are the free neutrons that are flowing around, both from the R-process event and from beta delayed neutron emission, before you don't have to take into account the neutron capture on daughters from the main event?
Yeah, so I think probably the easiest answer I could give to that, which is maybe a bit of a sidestepping the problem a bit, is that after about, say here, we were looking at 15 minutes, after you eclipse a time step that's, or a point in time where your neutrons are going to decay into protons before they have the opportunity to capture onto something else, would probably be, so they're being produced more slowly than they're decaying, would probably be the point where I would certainly start to feel more comfortable with this type of analysis. I'd say one thing we are looking to do, which can be immediately sort of reintegrated into this type of analysis, just not in this first analysis, is that insofar as you have, maybe I'll go back here, this time dependence that's allowed for these lambdas. If you took a more direct modeling approach, so from seed nuclei to nucleosynthesis to stability, and use that to infer some fixed or some neutron abundance as a function of time, some profile, some function that would return that and is fairly representative for the event you were looking at, you could then fold effectively this term here into an effective lambda, which is what the reactor burnup community would do. They would say that your neutron flux gives an effective decay that would bump your nuclei over one way or the other. And so that would be one way to sort of integrate those sort of latent neutron captures back into these simulations. And I think that would be probably the best way to proceed. Would be, in fact, not to ignore them, but to integrate them insofar as we could still do that and leave the other pieces of this in place.
Thanks. But so have you started to incorporate beta delayed neutrons as well? Since that's for the more neutron rich, that actually will give you new neutrons that are created after the main event. And so that 15 minutes is may not be a long enough time scale.
Well, so when I was just perusing the sort of like experimental nuclear data libraries, the longest known delayed neutron emitter that I could find had a half-life of about, say, a minute, which you could infer by even just by looking at the Q beta ends, for instance, and whether or not they have the right sign for this to proceed. But at some point in this analysis, you'll end up on a track that's strictly proceeds along an isobar towards a stable nucleus with no perturbing either reactions or decays that take you off of that chain. And so I think the point would be that the later you move into this sort of analysis, the more appropriate it becomes. So maybe it's not after an hour, but if you're trying to get a sense of where the abundances are with the things that are decaying are after, say, a day, for instance, I think it would certainly hold up there. I think the best course of action would be to investigate those points further on these shorter timescales of, hours to fractions of a day. Absolutely.
Thanks.
Okay, Gabrielle.
It's unclear to me if I correctly understood what you mean by isochronic evolution. If I understood that, basically what you are saying is that if you look at the evolution of the abundances at time scales of 1 day, they are basically determined by nuclei who have lifetimes of 1 day. So I understand that mathematically this is really what you want to achieve, but there are nuclear structure reasons why sometimes basically in some isotopic chains, you don't find half-lives of 1 day. You may have variations from hours to days. So physically, it may not be possible to achieve.
Yeah, of course, there's going to be perturbations about that idea. I mean, these half-lives, as you say, don't exist on a continuum. They're discretely defined. I think the point is rather that if you start from very, very short-lived, so things with half-lives of nanoseconds to milliseconds, eventually they're going to populate a nucleus that has something on time scale of, say, a second. And regardless of whether or not you started a millisecond or a nanosecond half-life nucleus, the uncertainties that if you write out the equations for what the population of that 1 second half-life nucleus is, you end up with delta errors in the exponent that are proportional to the uncertainty in the half-life or the full range in the half-lives that proceeded to produce it. So it's sort of as if you're maybe rolling down a hill and then the hill all of a sudden becomes very flat. At some point, everything's, gets to the bottom of the hill at the same time if you let it, roll out slow enough, I think. So it's, I think you can in fact show something along these lines mathematically. We just elected to just do direct simulations instead to illustrate the point. But yeah, absolutely. There's going to be some dispersion at any time step across, a handful of nuclei that might be populated with potentially very different half-lives.
Okay, looks like we don't have any more questions. Thank you, Trevor. And if you'll stop sharing, our next speaker is Gabrielle.
Yeah, I think we agree that Samuel Giuliani will give the talk. I was operated recently. I was not sure that I was able to make it for the talk.
Oh, that's no problem at all. Please go ahead.
Okay. Well, good afternoon or good morning, everybody. Yeah, as Gabriel mentioned, actually, he was unable to give this talk, and he actually asked me to present the results of our work, which are based on studying what is the role of translated nuclei and fission during the R process nucleosynthesis. And since this is already the third talk about fission on the R process, I assume there is no need for too much introduction about it. However, I would just like to add a few words to what Nicole and Cagino very nicely presented today. So we know from observations that actually the solar system and different metal pool stars show abundances of the actinides, uranium and thorium. So what this observation already suggests us is that the air process path must proceed through a region where fission may dominate, regardless of whatever is the main astrophysical site responsible for the production of air process elements. And indeed, actually, the idea that fission may play a relevant role during the air process was already suggested a long time ago. And here I was just highlighting few of the main features relating fission to the air process. For instance, it has been suggested that fission can be the main mechanism behind the robustness of air process abundances. this plot from Koropkin and collaborators showed that different trajectories describing different neutron star merged system and neutron star black hole system produce virtually identical abundance distribution due to the extreme neutron richness of the environment, which induce several fission cycling. Also, well, Nicole and Cancino nicely explain what is the role of fission in shaping their process abundances, particularly around the second peak, but that could be extended even further in terms of mass number, and also the role that fissioning nuclei can play in kilonova observations at timescales of several weeks. So what all this variety of phenomena is suggesting is that it is worth to look at what are the fission properties of very neutron-rich nuclei and try to understand how that properties may introduce some distinct signature in different observables related to the R process nucleosynthesis. So whenever we want to study actually the impact of fission on the R process, there are two main aspects that we have to consider. The first one, of course, is the astrophysical site where their process occurs. And this is because not only this determines the thermodynamic conditions at which where their process operates, but also because we need neutron-rich environments in order to allow their process path to reach the fissioning region. Of course, the second ingredients are the nuclear properties of these heavy and super heavy nuclei. So as we have seen in the previous talk, in order to perform nucleosynthesis calculations, we need to compute the nuclear properties across the whole nuclear chart. And this can only be done through global models, which actually are restricted to two main formalisms, either the microscopic model, such as the FRDM calculations that we have seen before, or energy density functions, that is the formulas that I'm going to use throughout this talk. So one of the main problems with these global models is that it is very difficult to assess what is or what are their systematic uncertainties. And therefore, one of the biggest challenges in current nuclear astrophysics is to understand how to propagate these systematic uncertainties throughout the nucleosynthesis calculations. Finally, the last point that I would like to make, and that was already raised by previous speakers, is that these two aspects are not completely independent. And what I mean with this is that the impact of particular nuclear properties strongly depends in the astrophysical sites that we are looking at. So in the rest of the talk, I will actually focus on neutron-rich material, like the one that you can find in tidal dynamical ejecta of neutron star mergers, or in viscous outflows in post-merger accretion disks. So for such kind of environments, we usually have neutron to seed ratios that are of the order of several hundreds that will allow the seed nuclei to capture several neutrons and beta decay, crossing the whole nuclear chart and reaching the region where fission dominates, splitting the nucleus in Lecter fragments and terminating, therefore, the R process path. So whenever we want to assess what is the impact of fission on the R process, there are actually three main questions that we should be able to answer. That are, the first one, of course, is where does fission occur? Which at the early stages of the evolution is mainly determined by the competition between neutron capture and neutron fission, but that later in times, it also depends on the competition between beta decay and beta delay fission, and of course, spontaneous fission. The second question is how much material do we accumulate in the fissioning region, which strongly depends on the neutron shell gaps and the beta decay half-lives of these nuclei, but of course is extremely sensitive to the thermodynamic conditions of the environments. And finally, the last ingredient that we need are the fragment distributions that are telling us which nuclei are populating from these heavy neutron-rich nuclei. So therefore, the main message that I wanted to bring with these slides is that in order to assess the impact of fission on their process, we need the global calculations of several nuclear properties, like for instance, masses, beta decay half-life, and neutron captures of these heavy and super heavy neutron-rich nuclei, which from a nuclear structure point of view is a big challenge. And the reason for that is that all these models have, the parameters of this model have been fitted to nuclei that are placed close to stability. And therefore, as I mentioned before, this fitting may introduce some systematic uncertainties which are not fully under control in this very exotic region of the nuclear chart. Therefore, what we would like to do in principle is to study how the different physical assumptions that we use in our models produce different results for the nuclear properties of these very exotic nuclei, and how these different nuclear properties have an impact on the air process nucleosynthesis. In this way, we try to make a connection between the air process nucleosynthesis and the fundamental nuclear physics that is governing these nuclei. However, one problem that we can face is that whatever we can find that is the relevant physics for nuclei close to stability may be not so relevant for very exotic nuclei. And for example, I would like to bring the case of triaxiality in fission. So for those of you that are not familiar with fission, it is actually well known that for stable actinides, triaxiality can play a very important role in reducing the fission barrier height. So this is shown here where the fission, in this plot on the right, where the fission barrier for 236 uranium is plotted as a function of deformation. So this black line here represent the calculations that we obtain when one imposes axial symmetry on the nucleus, while the yellow line represent the results that we can get when we allow the nucleus to undergo triaxial shapes. As you can see, there is a lowering of the fission barrier that is of several MeVs, which translates actually in a dramatic change for the neutron-induced fission cross-section that is plotted here on the left as a function of the neutron incident energy. However, if we try to repeat the same calculations for more neutron-rich nuclei that we may expect to be produced during their process and play a more important role, what we see is that there is still some impact of triaxiality in the fission barrier. However, its overall impact on the neutron cross-section is clearly much smaller. And we could try to extend this reasoning and argue that whatever are the systematic deviations that we find in our models between experimental data and predicted quantities actually may wash out when we look at very exotic regions of the nuclear chart. And at the same, in the same way, we could actually, we have to always to keep in mind that sometimes those models that better reproduce values close to the stability may introduce some systematics that propagates and could bring larger uncertainties in region of, in exotic region of the nuclear chart. So the message that I actually want to bring here is that global calculation using different models are strongly needed for air process calculations, because they allow us to really understand what are the systematic uncertainties in our estimation of the nuclear properties in the exotic region of the nuclear chart. So let's look then actually at how these systematic variations for fission properties look like. And probably the easiest starting point is to look at what are the predictions of the fission barrier, which, as Cagino and Nicole mentioned, is a very good proxy related to the stability of nuclei against fission. So here, the fission barrier height of 4 different models are depicted as a function of the proton and the neutron number. This red line here represents a nuclei with a neutron separation energy of 2 MeVs, which give a rough estimation of the location of their process path. So if we look from a very qualitative point of view, we can see that there are several resemblance between the different models, like for instance, the increase of the fission barriers around this neutron shell closure 184, or this region of vanishing fission barrier with this banana shape. However, from a quantitative point of view, we can see that actually the difference in the prediction between these models in the regions that are close to the air process path can be up to 5 MeVs. And if you remember the previous plot about the neutron cross-section and the fission barrier heights, you can see that actually this kind of difference can result in changes of several orders of magnitude in the neutron-induced fission cross-section. So already from these bare nuclear structure properties, there are some, we can extract actually some conclusions regarding what could be the possible formation of heavy and super heavy elements during the air process. So in order to do that, what we can do is to look at the so-called energy window for the neutron-induced fission, which is actually telling us what is the difference between the fission barrier height and the excitation energy at which the nucleus is, the compound nucleus is formed after capturing a neutron. As a very rough estimation, one can assume that below a value of 2 MeVs, usually neutron-induced fission should dominate over a neutron capture. So these are the same function as I was showing before, but now I'm representing this quantity always as a function of the proton and the neutron number. And what actually we can see is that all these models predict that in order to reach the heaviest part of the nuclear chart, their process path has to overcome this neutron shell closure at 184. But in order to do that, for most of the models, their process path will encounter a region of very low fission barriers where we can expect actually their process to terminate due to neutron-induced fission. However, there are some cases like D1M where the barriers are predicted to be larger, and therefore we could expect their process path to proceed towards the heaviest region of the nuclear chart. However, at some point, of course, neutron capture will exhaust, beta decay will start to dominate, and this material will start to decay towards stability. And in doing that, actually, it will find a region of very low fission barriers where we can expect that the progenitors of more stable heavy and super heavy nuclei will be destroyed by fission. One can see therefore that there is really a lot of information that one can extract already from just the bare calculation of nuclear properties. However, in order to really understand what is the impact of these systematic uncertainties, we have to use this nuclear input, plug it into nuclear network calculations, and see what are the resulting abundances and kilonova light curve. So what I'm going to do, okay, thanks. What I'm going to do in the next of the talk is to focus on the results produced by this BCPM energy density function. So what I'm doing here is compare our results with the other two models that have been widely used in nucleosynthesis calculations. Here, what we can see actually is that whenever we use these 3 different models in, for instance, and we study the air process nucleosynthesis obtained in tidal dynamical ejecta, we get at the time of the freeze out the following abundance distribution as a function of the proton and the neutron number. So we see that for HFB14 and BCPM, we have larger fission barriers, which actually allow the production of heaviest nuclei, while in the case of FRDM, their process is terminated at the neutron shell closure 184. Of course, this has a strong impact in the final air process abundances, where we can see the enhancement around the second peak that it was already discussed before. However, this impact of the fission property strongly depends in the astrophysical conditions For instance, if we now repeat the same calculation by looking at the accretion disk, which has a much smaller neutron to seed ratio, we see that the impact on the final abundances is much smaller due to the fact that whenever their process reach this region, most of the free neutrons are already exhausted and therefore less fissioning material is accumulated. We wanted to see actually what was the impact of this fission property also at early stages of the evolution. And what we found is actually that the presence of fissioning nuclei could have a strong impact on the evolution of neutron abundances at times after the freeze out. So if we assume actually that the free neutrons are in a quasi-equilibrium regime, we can then describe them using this formula here, where we single out the contribution from all the different channels that either release or absorb neutrons. If you look at this plot on the right, which is a rather busy one, but just ask you to focus on the green line here, you can see that actually the neutron abundances predicted by FRDM are more than 1 order of magnitude smaller than those predicted by HFB14 and BCPM. And this is actually due to the fact that these other two models have a large contribution of neutrons coming from fission, which either decrease the denominator or increase the numerator in this expression here. And this increase of the neutron number densities has a strong impact on the kilonova light curve, since actually what it does is it destroys the progenitors of 254 californium in the case of BCPM by late neutron-induced fission. This is similar to what we can see, for instance, in the nuclear reactors where decay chains destroy all the fissile nuclei. On the other hand, we see that very large, models predicting very large fission barriers like HFB14 can accumulate a large amount of 254 californium, which produces these huge bumps in the radioactive heating rates. So the conclusions that I would like to bring with these slides is that several studies seem to suggest that kilonova light curves are extremely sensitive to the nuclear properties at the neutron shell closure 184 and mass number 254, which actually is a very important result because this region of the nuclear chart is not going to be accessible in the next year by the future radioactive beam facilities, as we can see in this plot, and that Artemis will talk more in the next talk. Well, as Nicole already mentioned, this is something that this kind of study has also been done by other groups, where we can see the large variations of the effective heating rate at timescales of several weeks. And I would like to conclude this talk by showing what is the impact of beta decay rates on fission. So we know actually that the impact of the beta decay, or what are the relevant beta decay lifetimes, depends a lot in the kind of observable that we look at. For instance, if we take one set of beta decay rates and increase or decrease the rates by 1 order of magnitude that are above a certain value, for instance, 3 seconds, we can see that the abundances are barely changed, while instead the heating rates can suffer a lot of variation due to the fact that either we change the competition between fission and beta decay, or we are just changing the time scale at which these fissioning nuclei are produced. This, of course, is a very big challenge for nuclear structure calculations because, as this plot from Caroline Robin from GSI show, the calculation of these beta decay rates that are closer to stability or that have longer lifetime are more uncertain because the Q beta values are smaller, and therefore the rate strongly depends on tiny difference on the strength distributions. And since I actually at the end of my time, I will just conclude here my talk and just recall I will just leave here the conclusions for you to read, and thank, of course, all the people who collaborate in this work. Thank you all so much.
Okay, thank you, Samuel. I don't see any hand raised, but so I'll go ahead and ask a question. For your fission cross-section calculations that you showed early on, in conjunction with the barrier heights, there was like a double panel. Could you maybe comment, yeah, for the uranium and also I think you had a fermium isotope. Could you just maybe comment on the model you guys are using here to calculate the cross-section?
Yeah, so actually this is just done through standard Hauser-Feshbach statistical calculation. In this case, we plug it into the Thales reaction code. So basically what we have here is, well, as you well know, this is giving us what is the transmission coefficient for fission, which basically depends on what is the tunneling probability of the nucleus below the barrier.
So you're using like a Heil-Wheeler, I mean, you're
yeah, exactly. So
okay.
What we do is, well, actually we do it using in principle, the full WKB probability or semi-classical approach, sorry.
Okay, I gotcha, thanks. Okay, I don't see anybody else. Let me check the chat here. I also had another question. You showed the this really nice analysis of the free neutrons coming from all of these different channels. Yeah, this plot here. So you guys are seeing a quite substantial uptick of the free neutrons at late times after like 10 to the 3 seconds. What is that coming from? Maybe I'm missing it here in the figure.
Yeah. So actually, let's say the part that is more relevant is more around something between 1 and let's say 100 seconds. So right after the freeze out. So actually, what is happening here is that the evolution of the free neutron abundances strongly depends in the different channels capturing and releasing neutrons, right? And in that case, what one has is that fission can release several neutrons, which actually, whenever your neutron abundance distribution starts to strongly decrease, can strongly be varied just by a tiny amount of fissioning nuclei contributing to your free neutron abundances. So for instance, this red line here represent the free neutron contribution from neutron-induced fission in HFB14 that one can see that is much higher than the one that one gets with FRDM plus Thomas Fermi, just to the fact that we have a lot of fissioning nuclei which suffer neutron-induced fission and therefore release a lot of neutrons. And the same the case is for beta delay fission and spontaneous fission and so on. I don't know if that answered your question, Matthew.
Yeah, I guess I was just a little confused with why this. So the dotted curve there is the free neutron abundance. Is that correct? And
yeah. So the dot. Okay. Yeah. The black points are the free neutron abundance, so the one obtained in the calculation, and the green line is just the calculation that we obtain assuming this quasi-equilibrium regime. So this quasi-equilibrium regime is just that you have your total evolution of the neutron abundance is very small, but what you have is a large contribution from targets, from nuclei releasing and absorbing neutrons.
Yeah, so I mean, like, the half-life of a free neutron is like something like 10 to the 3 seconds.
Oh, yeah, yeah.
So what you're showing here, it seems to say, if I'm understanding this plot correctly, is that your fissioning systems are releasing a whole lot of neutrons for a really long time, and then finally the decay of the free neutrons starts taking over.
Yeah.
Okay. Yeah, it's really fascinating. Okay, I don't see any other questions. Oh, wait. Looks like Kelsey has something in the chat. Kelsey, did you want to unmute and ask your question?
Sure, thanks. That was a great talk. I was just wondering, just when you studied the variation of the beta decay rates, were there any specific isotopes that kind of stood out as having interesting competition with the other decays?
You mean in terms of fissioning isotopes?
Yeah, or you know, alpha decays, or just if there were any specific ones that stood out.
Yeah, so actually, nothing new to what actually, well, I must admit, I didn't look in details of the composition, but actually I don't think that will be much different from what has already been analyzed by, for instance, your work or the one from Mengru Wu. So in terms of alpha decay, we don't really see much difference in a strong impact when we vary these beta decay rates. So from that point of view, it really only changes those nuclei that we already know that are going to be relevant for at late times for their process. It just changes when you are producing it, either later or earlier.
Great, thanks.
Thank you.
Okay, thank you, Samuel, for a nice talk. Up next, we have our final speaker, Artemis.
Thanks very much for the invitation, and I will apologize I was not able to join the rest of the meeting the week. I am currently at Argonne National Lab running an experiment, and it's been quite a busy week with various issues, but also very nice data, very relevant to what I'm talking about. So, but I don't have results after, since we're still running. Let me share my screen. There we go. So this session this morning was more focused on fission, and I wish I could have some experimental data on fission in the region that is of interest for the R process, but I think experimentally we're not there yet. My work has been focused more on the neutron capture constraints for the R process, and that's what I'll talk about today. And I've given various versions of this talk many times, so I'll just start up front with saying what to expect, what's new in this talk. So I'll talk about some new experiments we've been doing here at Argonne at Caribou. So we're very excited to have access to a whole lot of nuclei we didn't have access before at the NSCL. I'll introduce a new method we developed in the last year or so that helps. It's in the same direction, constraining neutron captures. But it's helping us remove some of the theory dependencies we had in the past. And of course, the exciting thing about the future going towards Adrift. So I'm sure during the week, these things have been discussed a lot. And even today, I heard a lot about what nuclear physics inputs we need. So I'm not going to go into detail about any of these. My group has been focusing on beta decay rates and neutron capture rates. And today I'll focus on the latter, although I'm happy to discuss beta decays and what we're doing with that. So neutron captures are just hard to measure experimentally. They're almost impossible to measure experimentally on a short-lived nucleus. And so what we've been doing, several groups, we've been trying to constrain them experimentally. So if you're not able to measure it directly, at least you provide strong constraints that are relevant for whatever limits or whatever uncertainties you can accept within the astrophysical calculations. And so we've seen that if we can constrain the neutron captures within a factor of 2, it's already a very good constraint. We don't need right now to measure them at the 10% level, for example. And so let's say that's our general goal, is to constrain as many of the neutron captures as possible within a factor of 2. We'll never be able to measure all of them, but at least measure a few at various masses and far from stability, so we can constrain the nuclear models. So that's kind of the summary of what we're trying to do. So how we're trying to do that, to get there, I want to show the very simple picture of how one calculates neutron capture rates. And these are statistical neutron capture rates. So if we're talking about regions close to magic numbers or close to the drip line where the statistical model approach doesn't work, then what I'm talking about also doesn't work. We need to use different experimental techniques. So the idea is that if you would have a neutron capture populating some kind of a compound nucleus, the main ingredients you need to calculate this neutron capture are the nuclear level density, the gamma ray strength function for how your gamma rays are flowing down, and of course the optical model potential between the neutron and the nucleus. It turns out that the optical model potential is not so important in the regions that we have access to. It does become more important as you go further away from stability, but the two main ingredients that cause the large uncertainties in these calculations are the level density and the gamma strength. And so these are the two that we're trying to constrain. We've developed, now it's been 6 years, so we've developed a technique called the beta Oslo, which is based on a well-known method called the Oslo method, which I'll just very briefly introduce. And we combine that with total absorption spectroscopy, which is a beta decay method. And that helps us to apply this Oslo method and extract these important quantities using beta decay. The advantage of beta decay is that you can now go much further away from stability compared to anything you could do with the reactions-based technique. So very briefly, the Oslo method uses experimental data that look like this, where you want to know the excitation energy of the nucleus you're populating versus the gamma ray energies that are coming out of the de-excitations. And if you have this information, you can go through a couple of steps to figure out, first of all, what is the distribution of primary gamma rays. So from every excitation energy, what is the distribution of gamma rays as a function of energy? And this quantity, this probability distribution, depends on both the nuclear level density, which is rho here, and the transmission coefficient where the gamma ray strength function enters. They do come out as a product, and this will become important a little bit later in the talk. So then you need external information, this normalization, to be able to separate them out and actually get the information you need. But once you do that, the Oslo group has shown previously that once you extract this information and you go and get a neutron capture calculation, it agrees very nicely with experimental data. Now, this is a textbook case of what one can do with this method. This is a very heavy nucleus, very heavy, very large level density. So there are limitations in what you can apply this for. And so we've been investigating what we can do in terms of beta decay and going far from stability. So with the beta decay, it's exactly the same idea. Instead of populating the nucleus using a reaction and getting the compound nucleus, we just now come from the beta decay side. So you're feeding the various states all the way to high energies. Typically, you go all the way to the neutron separation energy somewhere here. Sometimes we've seen going a little bit higher than that. And again, once you feed the nucleus you're interested in, you can get the excitation energy, you can get the individual gamma rays, and apply the method I just described very briefly. And again, we can do these experiments with beam intensities down to about 1 particle per second, which it gives you several more steps away from stability compared to like a 10 to the 4 particles per second you would need for a reactions-based experiment. So the way we do these experiments, if you're just curious about the equipment, I'll go very briefly. The heart of our setup is the SUN detector. It's a summing sodium iodide. It's a very large detector that detects all gamma rays that are coming out. So this way we can get the excitation energy we're interested in. And it's also segmented so we can get the individual gamma rays as well. We combine it with various other pieces of equipment to do coincidences, remove the background, tag our beam, identify our beam. So again, all of these I'm happy to discuss, but I don't want to spend too much time on them right now. We've done a lot of experiments at the NSCL at Michigan State University. This is the facility, and very briefly to say that this facility was because it has now closed. As of let's say 9 months ago, it has closed, and we're now in the transition period to go into effort. But the facility would produce radioactive beams based on 2 cyclotrons, and the beams were at about 150 MeV per nucleon energy. And we could use those beams directly, these fast beams, directly into our setup and look for their decay, or we could slow them down and purify the beams into this gas stopping area, and again, do these experiments with stop beams. As I said on my first slide, recently, right before the pandemic, we moved the whole equipment, the whole setup to Argonne National Lab. And the reason for that is because of the unique capabilities you get with the Caribou source, which is sitting right here. So this is a californium-252 spontaneous fission source. It gives you these nice fission fragment distributions. And so now some of these isotopes are actually a lot more intense than what we could get at the NSCL. And so we decided to take advantage of these opportunities and do some measurements here. So we moved our equipment. This is a picture from 2 years ago. We moved our equipment here, Sun, the whole tape system that goes with Sun. And we've now run 2 experimental campaigns, one last February before the pandemic, and then everything was on pause for a while. And we are right now running our first experiment, post-pandemic experiment. Okay, so as I said, a lot of the things we've been doing is we've been doing a lot of new measurements, but also working on validating and convincing ourselves and the community that this idea, this crazy idea of using beta decays to get anything about compound nuclei is actually working. And so I'll just briefly show you the validation, the recent validation we did, and it was published a couple of years ago, where we populate the same nucleus. This is titanium-51, pretty light nucleus, but this was the one that we could do with 2 techniques. We could do it with beta decay, so from scandium-51, and we could also do it with a DP reaction. So the top spectra here, let's just focus on the primary distribution. This is what you get with the beta decay, and this is what you get with the DP, and they are very different. You expect to populate different states. You do expect the spectra to look very different between them. But then we go through all the corrections for the spins, for what kind of states you're expecting to populate with each type of population mechanism. And if you do that, you actually get the same answer. So in these pictures, blue is coming from beta decay and black is coming from DP. Again, it's a light nucleus, it's a very small range, but to the extent that we could use this technique to validate, they seem to agree very well. So both the gamma ray strength, this plot, and the nuclear level density. We are working on getting a similar validation to much heavier masses, but again, this is what we have so far. And we also extracted a neutron capture, which may or may not be so meaningful at this point, because you see the experimental points have large fluctuations. These are direct measurements. And so there's probably resonances, it's a low level density, but if you go to the higher energies where it starts to become a little more statistical, we do get a nice agreement with the data. So we're optimistic that this is actually working very well. We need to continue the work on proving that. But in the meantime, assuming that this works very well, we have applied the technique to quite a few neutron captures. And we've been focusing so far on lighter masses because they are easier to measure. And these were the beams that were available at the NSCL. So I show you a few examples here where the darker area is what you extract, the neutron capture you extract constrained from experimental data. And the blue area is what you would get without those experimental constraints, just based on theory predictions. So we provide pretty strong constraints for the cases that we've done so far. One interesting case we did was do the whole chain of nickel isotopes. And then this is kind of the heart of what we're trying to do, is do the systematic so we can provide constraints to nuclear theory and then use it in our process calculations. And so here you can see 5 different isotopes of nickel neutron capture reactions. You see the 2 odd isotopes are sitting higher than the even isotopes as expected. And then the even isotopes are all kind of falling on top of each other here. But we do see different odd even effects. The intensity of these, or the differences between these odd even effects, is not exactly what theory predicts. And I will come back to these odd even effects later, but this is just very preliminary, it's not published yet. But this is an interesting result that we're looking into. Okay, so let's go to the new things. As I mentioned before, normalizations are a big part of what we do with the Oslo analysis. And we need 3 external normalizations outside of our experimental measurements. We need the low-lying levels to normalize at the low energies for our level density. And those are typically known for the cases that we get access to. Other experiments have been done already, and those are already known. The second point we need is the level density at the neutron separation energy, or somewhere at higher energies, somewhere up here. So we can normalize, we can get a slope of the level density. So previously this was done with measurements of D0s at high energies, and that's only for stable isotopes. You don't have this information for radioactive isotopes. And so the only thing we could do at the time was to use theory. We used all available theoretical models, and we used all of them, and that added a larger uncertainty to our measurement. And of course, it added a theory dependence to our measurements. So this is something we want to get rid of. And then finally, on the gamma ray strength function, we use either the radiative width or giant resonance data, where whatever we have available. Again, it's far from stability. There's limited data available, but we use what we can. So what I'll talk about is we figured out a way to get rid of this part, the second part. The dependence on dependence on theory for that level density point. And this is done through a method that's called the shape method. It's there was some information or some similar introduction of a method that was called the ratio method in the past. They're all very similar, but we ended up with a name that's called the shape method because what the method gives you is the shape of the gamma ray strength function. The idea is rather simple, actually. You start with an excitation energy, and if you have the decay of a gamma ray going to some discrete level that you can just measure directly, and then a decay of a second gamma ray that goes to a different discrete level, if the 2 levels have the exact same spin and parity, they're all starting from the same excitation energy, then everything is the same. The level density distribution, the spin distribution, everything is the same. And the only thing that is different between them is the energy. So if you keep doing this for various excitation energies and you move this lower and lower and lower, then you can get this information, this energy dependence for different energies. And you can just sew the data points together or connect all of those data points together to get the shape of the gamma ray strength function. And this is what this was done in the original paper by Maris Widiging from 2012. And this was for a molybdenum isotope. And the same thing happened. I realize here that I don't have my isotopes marked, but this is iron 56 and this is molybdenum 95. But both of those applications the method seems to work very well and compared to other experimental data. And so this is, again, a model independent way of getting the shape, the energy dependence of your gamma ray strength.
4 minutes.
So this is exciting. What's that?
4 minutes.
Thank you. So this is exciting because now if we combine this with the Oslo method analysis, we can get the level density, again, with the slope of the level density with no external information. And this is what we've done. So we applied this, I'll kind of skip this. We applied this on experimental data we already had on gallium 76 into germanium 76, just to check that it actually works also with beta decay and all the constraints you get, again, with the beta decay. And it looks like it's working very well. The black points are the new data, and they agree very nicely with the red points. Again, if you go to very low energies, this nucleus is not completely statistical, so you get some fluctuations. But in the region that we trust that it's quite statistical, then you get a nice agreement. We applied this on new data. That was old data. We ran a new experiment at Argonne National Lab on bromine beating krypton 88. And this also looks very nice. So this is now our new fresh results. They're submitted, but not published. So again, these are the black data points in agreement with these are other different nuclei, not the krypton 88, but just kind of to compare and see how it compares. And this is our exciting new result. These are all the black points here, experimental points completely independent from any theory. And we compare them to the available theoretical models just to see how they compare. So this particular nucleus is not the most exciting nucleus because it's just one step from stability. So the models are well constrained and they more or less agree with the experimental data. But if we would apply these to 1 or 2 steps further away, then the models just completely disagree from each other. And then we could give, choose which of these models work better and which not. This can be seen in this picture here, where we have various nuclear level density models. It's a ratio all compared to this level density model 4. It's just kind of an easier way to plot this. And this is again what I wanted to point out in terms of the odd even effects I mentioned earlier. There are huge differences in the odd even effects for all of these models. And so it's very important to go in and check and compare with experimental data and choose which one works better and which one. So yeah, we are right now at Argonne and we are doing more measurements. As I said, our goal is to try to push this further to heavier masses. We've so far have been focusing more on the lighter masses. And so here the boxes show you what we're doing right now, which is this region. And we're starting tomorrow with this region. And then we have 2 more experimental campaigns, one a little bit lower and one a little bit higher. And so we are extending, this is exciting, we're extending to much heavier masses at Argonne. And of course, a step further is going into the FRIP era. And this is a picture that shows the predicted rates, beam rates for FRIP. Where we expect to be able to apply this method for neutron captures is this yellow region right here. And so you see on the picture, this yellow region and anything less exotic, we would be able to apply this technique. So we do reach the R process path, we will be able to approach and provide constraints directly related to the R process. And to start with, we submitted our first proposal to the FRIP PAC, which meets in 3 weeks or something like that. So this is, we're fingers crossed, we're all holding our breath for what gets approved and what doesn't. So we will use the FRIP decay station. Instead of SUN, we will use MTAS. They are very similar detectors, similar capabilities. And so we will use the same technique. These are the nuclei we proposed. You can see them here. These are the red dots sitting on top of Matt's and Rebecca's sensitivity study. And so we are able to go right in the region that is important around tin. You can see here a zoomed in version and in the region that is important. And so, yeah, we're very excited to, hopefully the proposal will get approved and we're excited to be able to apply this, to do these measurements. Actually, right after we submitted the proposal, the science paper that also Nicole mentioned earlier in the day came out. And we immediately contacted Matt and the rest of the group to see what neutron captures we could measure that would have a big impact on the iodine-129 abundance. So we can better constrain, from the nuclear physics point of view, better constrain these predictions. And as it turns out, the nuclei that are important for iodine-129 are the exact same nuclei that we already had in our FRIP proposal. So now there's a second strong motivation, very specific, to iodine-129. So again, fingers crossed, hopefully this will get approved. If not, I mean, there's so many good FRIP proposals. If not, we will definitely submit it again the next round. So I hope I didn't go too fast and I showed you some of the work we're doing with the Bethe-Oslo method and trying to constrain neutron capture reactions. We did develop a new technique to remove some of the model dependency from our measurements. So we are excited about the shape method and trying to apply it to more nuclei. We continue our measurements right now at Caribou, and we are pushing towards heavier masses. And of course, FRIP is coming up and we are looking forward to the first experiments there. And I'll finish with a list of collaborators, which keeps changing all the time. I hope I captured everyone. And thank you very much for your attention.
Okay, thank you, Artemis, for that really nice talk. I'll ask a quick question because I don't see any hands just yet. This is the first I've heard of the shape method. It's really fascinating. Do you have enough information there to get something like a parity dependent level density? Is that something you guys can do, since you essentially gate on the different levels? Because this is something in theory that would be, you know, very valuable to us if we could have this information.
Yeah, that's a good question. We've been looking at this, so I'll just show this. You need to be feeding the discrete levels in some significant way to be able to apply this technique. And to first order, you need to be feeding 2 levels of the same spin and parity. Actually, our collaborators, Maris Widiging from South Africa and Cecilia and Magne from Oslo, they have applied this method with reactions on different spins and different parities. And if you do the right corrections, actually, it still works. But the limitations we have is just what nature gives us as, you know, what states are fed in the beta decay. The advantage of the beta decay is that it's very selective. And so you do populate specific parity, as you're interested in the parity. You do populate specific parities at the top, you know, at the higher levels, high excitation energies. And so then you, in principle, you could differentiate between, like, if it's M1 or E1, depending on what states you're populating at the bottom. But it is limited. So we do see very few of these states. So we're still looking for, you know, if we can see these differences or nucleus that populates more than just a couple of states, so we can do these comparisons.
Okay, really fascinating. And you also mentioned this odd even behavior you found in the nickel isotopes, where you have even captures that are, you know, significantly slower than the odd capture rates. I mean, that's something we do find in theory. And one of the things I've been fiddling with our process calculations is that it seems like you need the less odd even staggering than what you obtain in with current theories. If you don't want to have this odd even staggering show up in your final abundances. Is that what you guys are observing? Or I mean, it seems like
interesting.
Yeah,
I don't know yet for the nickels. We wanted to take a closer look, but we haven't done that yet. It's the usual problem. A student finished and graduated, so we're still, everything is slower. But yeah, you're absolutely right, and we see this, like here, everything is compared to level density 4, and then so any fluctuations, odd even effects you see here are on top of what level density 4 fluctuations you already have. So this just gives you an idea that there is a huge variation in what the models predict in terms of odd even staggering. We were able to measure this data point right now, so we are trying to push further out. But yeah, I think if we can make it 2 or 3 neutrons more, then we'll already be able to be in the sensitive region to compare.
Yeah, that's really fascinating. Okay, I don't see any other questions from the chat. I think everybody's tired now. So many talks today. But anyways, I'd like to thank all of the speakers. I'm not sure if Chris maybe wants to give some closing remarks to our workshop.
Yeah, I was just going to thank all of the speakers and the chairs and Michaela at ECT Star for all the help. I think this was a really successful meeting. I enjoyed the talks immensely. Thank you, everybody, for a great meeting.